everybody. I hope you've all really enjoyed the conference so far. It's a pleasure to join you again today. My name is Jodie Howlett. I'm currently a young graduate trainee at ESA. And today I'll be talking to you about how to set yourself up for a space career. So I'll first talk you through my background and journey to a space career. And I want to share with you some things that I've picked up so far during my early career about events and conferences, skills and training, work experience, and membership and volunteer opportunities. So really, I want to kind of get you guys up to speed with different opportunities you can get involved in order to gain more insight and experience in the space sector. So this is what my journey towards a space career looks like. So I kind of started out by studying mechanical engineering at uni. So I started uni in 2014 and throughout my studies I did as many internships as I could. So I worked mainly in biomedical fields and also a bit of aerospace engineering. And really, it wasn't until I attended this conference in 2018 that I realised that there were so many opportunities in the space sector. And it was at that point when I actually started then to consider space as a career route for me. So that was my first introduction to space, and I was keen to know more. So I went away and I found ESA Academy, and I applied to their spacecraft operations training course. I managed to get onto that, and I went to Belgium for 4 days and did the training. I thought, yeah, space is definitely for me. This is what I want to do as a career. So I went back to my university and had a look at any opportunities that were available to learn more about the space sector. And my careers team kind of suggested that there was a career mentoring program where I could be paired with a mentor working at Reaction Engines. So I received mentoring for a year from a project manager at Reaction Engines, so gained some more insight into the sector there. I then applied to the International Space University. So I applied to the Space Studies program that they run, which is essentially a 9-week professional development course, and you learn about many different aspects of space. So for me, it wasn't just about engineering, but it was also about law, humanities, space medicine, many other aspects. And that was a fantastic experience for me to really throw myself into the world of space. And then I applied to ESA, to the Young Graduate Trainee Programme, which I'm currently doing at the moment. I work at the European Space Operations Centre in Germany. And to the bottom right there, you can see a nice picture that I got from one of the solar orbiter simulations that took place last year. And that's me in the main control room. So super exciting. So as I mentioned, I want to share with you guys some of the things that I've picked up on over the past couple of years on what you can get involved in. So first of all, I want to look at events and conferences and talk to you a bit about what you can do here. So first of all, if any of you use LinkedIn, hopefully after my workshop yesterday, you'll all be getting involved with LinkedIn a bit more now. You can go to the My Network section and you'll see that there will be online events suggested for you. So if you follow pages and groups towards space, then you'll likely see some events on space here listed. There's a number of other things you can do to follow events as well. So for example, Astroverse. If you sign up to these, you'll receive a monthly newsletter to your inbox listing all of the different space events taking place in the UK that you can attend. Space Agenda is kind of similar. It's more global, so you'll see from all over the world the different events and conferences you can attend. Space Pals is a great page to follow as well. I follow their Facebook page, and they deliver live webinars with different space experts from all over the world, talking about various topics. And yeah, there's a number of events and conferences listed here that you can go and take a look at for yourselves. I highly recommend all of these. So then thinking about skills, so what kind of skills do you need then to go and pursue a career in the UK space sector? Well, just recently, this report was published by the UK Space Agency, so just a few days ago, actually. So very recent information on the skills required at the moment. And in here we get kind of a nice overview of the main skills gaps as well. So just here we can see a list of what the participating organisations in this research have listed as their main areas of skills gaps for the more managerial and entrepreneurial skills. So we see things like project management, teamwork, leadership are all really highly in demand skills at the moment in the UK space sector. And then looking as well towards the more technical engineering skills, we see things like software engineering, systems engineering, electronics, AI, machine learning, data analytics. So all of these skills really are key at the moment and really in high demand. So this kind of information could be really helpful for you guys to inform you of the kind of skills that companies look for at the moment. And following on from that, it's then important to consider what kind of training can I do to upskill in some of these areas. So I've listed here a few examples of where you can get some training. So I mentioned that I took part in an ESA Academy course. They offer a lot of online courses at the moment. So for me, I had to go to Belgium at the time, but at the moment they're currently running it all online. They also have a lot of hands-on projects you can get involved in as well. So things like building CubeSats or running experiments in microgravity. So yeah, there's a load of things that you can read up on with ESA Academy and get involved in. With ISU, I've listed here a few examples of some of the courses and programs that they offer. So I mentioned that I took part in the Space Studies program. They also offer a master's year in space studies, which includes an internship in a space organisation. And they also run an online interactive space program as well. UMITSAT have a number of online short courses. So you can, for example, learn how to make use of Copernicus satellite data, how to apply that and run data analytics, covering different contexts as well. And then AGI have a number of free training and certifications in some of their tools. So things like Systems Toolkit, for example, I took part in a certification in that just recently. So those kind of courses are great if you're interested in the more technical systems engineering side of things. And then don't forget as well that there are, of course, a number of online training providers, more broadly speaking, that you can look at as well to follow space-specific courses. With work experience, so I've tried to be kind of specific to the space sector here. And the best example really that I can think of is the Space Placements in Industry scheme. So with this, if you become a spintern, as it's known, you will get the opportunity as an undergraduate to go and work in a UK space company and to work on real projects and gain that professional experience. So I highly recommend that you give that a search online. Space Careers as well is another great one. It's a place you can visit to find additional careers resources and also to see current job openings, internships, placements, that kind of thing. And yeah, if the year in industry as well is an option on your course, I highly recommend you take part in that. So you don't necessarily have to go and work in a space organisation during your studies, but any kind of professional experience you can gain is really a great asset, and it's an opportunity to gain transferable skills. With the Brooke Owens Fellowship, so this one is a programme specifically for women who are interested in the space sector, and want to apply to receive mentorship and to take part in a paid internship, which could be across the globe as well, not just limited to the UK, but you can potentially do an internship overseas with this. And then finally, I wanted to just mention some recent news about the UK space industry and how it's kind of setting up engineering apprenticeships at the moment. So for any of you considering an apprenticeship as a potential next step in your career, this could be a great opportunity for you as well to get engaged in the UK space sector. So here I've listed some of the different organisations where you can gain membership and also take part in volunteering positions potentially. So UK SEDS, of course, have organised today's conference, and they have many different branches all over the UK. So take a look at them, see where you can get involved. Space Generation Advisory Council are a fantastic organisation to sign up initially for membership and to take a look at the different events that they're running. You can apply for events and conferences through them, workshops. I think they offer funding as well for various things. And yeah, so there's a number of different programs they run. Women in Aerospace Europe are a great one to look at as well. If you're a woman interested in the space sector, they offer a range of events and activities across Europe. Royal Aeronautical Society, British Interplanetary Society, both of those again offer a lot of events and conferences that you can attend and get involved in, and also potential for awards and grants as well. So some final words from me. Firstly, it's important to remember that space is interdisciplinary. So it doesn't matter if you don't currently study a highly technical subject, or you're not an engineer or a technical person. You've seen, as I've shown, that there are a huge demand for many different skills in the space sector at the moment, not just technical. Secondly, get involved in things. So really make an effort to actually reach out and put yourself forward for opportunities. But don't worry if you can't do everything. That's really not an expectation. So don't take on too much. Just get involved maybe in 2 or 3 different things and see where it takes you. And thirdly, make use of your university's careers team as well. I'm really glad that I did this during my time at uni. I got some great tips on the application processes with different companies, and how to better present my CV and to communicate my soft and technical skills in different interviews. And you may find that they offer different awards and grants potentially to be able to fund some of the space specific opportunities that you might come across during your studies. So really that was kind of an overview of what I've picked up on as things you can get involved in your early career. But if you guys have more suggestions, I'm sure several of you will know more things to get involved in. Share them with each other. There's a Discord channel specific for this talk. So go there and post any ideas you have and let people know what they can get involved in. Thanks very much for attending today. I'll be available all day on Discord for questions, so feel free to reach out to me on there.
Good morning, everyone. Welcome back to day 2 of the 2021 National Student Space Conference. This is set to be another exciting day of the conference. We hope that you enjoyed yesterday. We're all really excited and really pleased to see you all engaging on all the different platforms we have. Quick reminder on that note about the hashtags we're using on Twitter and all the other social media platforms. We have NSSC 2021, hashtag NSSC beverage for your spacey drink, mugs, anything you want to share. NSSC fashion for any spacey clothing. Hashtag NSSC art for your amazing art creations. There were some great ones yesterday, and we hope to be sharing some more yesterday. And there's one more, which is hashtag NSSC. I can't remember what it is. Antonio. There's one more. Look out for it. I apologize for that. There's going to be conundrums throughout the day as well, so do those. They're good fun. Just to mention also that the networking functionality for the attendees, unfortunately, is down today. We had some issues with the careers fair, but they will be fixed. So make the most of the careers fair, but the attendee-to-attendee networking has been sacrificed for that. But the Discord is going really well. It's great to see so many people engaging on there. So head over to Discord if you haven't already and you are able to. I'm just going to quickly run through the program for the day. So thank you, first of all, to Jodie for an amazing Space Career Workshop to get us started. Really valuable advice for anyone looking to start their career in the space sector. So catch up on that if you just missed the start of the day. That'll be on YouTube later on. Thank you to Jodie. So in our first stream, we've got 2 exciting talks. One from Dr. Paul Rimmer on the recent possible discovery of pH3 in Venus's atmosphere. We then also have a talk from Grace Richards on Enceladus's surface. And on stream 2 at that time, we have our first live panel of the day, which is on the UK space sector and whether we are setting the right goals and strategies for the next decade. So that's set to be a really exciting discussion with some really key players in the industry there. We then have our keynote for Sunday, and that is given by Professor Yuichi Tsuda, and that is on the Hayabusa 2 mission, which is the Japanese Space Agency's flagship mission that was launched very recently and came back late last year with samples from an asteroid. Yuichi will be joining us for a live Q&A after that. So make sure to submit your questions for him. I'm really excited about that. Following that, on stream 1, we have a stream of some fast stream talks on space manufacturing. A variety of areas of manufacturing in space, be it on the moon, in orbit, or in other places in space. And then opposing that, on stream 2, we have an amazing workshop given by Avona, who are a space recruitment company, and they'll be answering all your questions about what you can do to set yourself up and give yourself the best chance of succeeding in a space career and getting that job that you dream of. We then be going to lunch at a rather awkward time of 12:33, and then coming back in the afternoon for 2 talks from 2 PhD students. So we're really excited this year to put out a call for 2 PhD students to submit abstracts to, because we recognise that this year we have a great opportunity being online for people who wouldn't normally get to present to such a large audience to present. And we're really excited to have Zaria and Clément presenting their work later on. We're also excited to see our corporate partner for the year ahead, UK Quantum Technology Hub Centres and Timing, presenting all the opportunities around quantum technology in space. That will start at 1:20 this afternoon, and the different career opportunities in that. And finally, another nice variety of talks in the late afternoon. We have some on climate science and space medicine, as well as a live panel on space debris. So really looking forward to that. And just to end off the day, we have a short closing. And if you haven't signed up for the UKSET AGM, if you're a UKSET member, then check your welcome email this morning, and that will follow at the end of the day at 3:30 this afternoon. I think that is all from me for the welcome, and I will now just introduce what we have coming up next. So on stream 1, we have a talk from Thales Alenia Space, and they're going to be showing you their amazing AR and VR technology that they use in space engineering. On stream 2, we have UK Space, which is the trade body for the UK space sector. They are going to be setting the scene really for the panel that follows immediately. So they're both set to be amazing panels and talks, and I will be back later on for our keynote talk, and I look forward to seeing you there. Enjoy the day. Bye, everyone. See you soon.
Welcome. My name is Simon Wheeler and I am the Engineering Manager for Software and EGSE at Thales Alenia Space UK. Today I'm going to show you some of the current and future work we are doing with mixed reality solutions. With 17 locations across the globe and combining 40 years of experience, Thales Alenia Space design and deliver high technology solutions for telecommunications, navigation, Earth observation, environmental management, exploration, science and orbital infrastructures. Since opening its UK operation in Bristol in 2014, our highly experienced European Space Agency trained technicians continue to develop breakthrough innovations and solve complex challenges to contribute to the world's most advanced space missions. Teams design remote sensing instruments, build technology demonstrators and test electronic systems for onboard spaceflight hardware. In addition to Bristol are Thales Alenia Space's satellite propulsion design and engineering teams in Harwell Science and Innovation Campus and the Propulsion Integration Centre in Thales Belfast. Together these experts design and build propulsion module systems for all of Thales Alenia Space's satellites, including the UK's first all-electric propulsion systems module for the next generation of telecommunications satellites. When we talk about mixed reality, currently we refer to two similar technologies. Virtual reality allows for a fully immersive three-dimensional environment, whereas augmented reality allows us to enhance the real world with virtual constructs. First of all, we'll start with VR. Welcome to the virtual Thales Alenia Space orbital platform. In front of you is an object I'm sure you will all recognise, the International Space Station. The ISS represents real collaboration from many countries across the globe, creating humans' only current orbital platform. Opportunities to take part in missions start with a bid presentation to win the work. Traditionally, this has been a paper exercise, but virtual reality now allows us to show the customer what we will deliver. It allows the customer to get a physical feel for the final assembly and build confidence in what we are proposing. This is the bare interior of the US modules on the ISS. During the design phase of a mission, VR can be used to really get inside a design to check how it will function. Currently TAS are working with ESA astronauts in VR to plan the interior of the Lunar Gateway Station. It allows the humans who will be relying on the environment and systems to have a detailed input into the design from the very beginning. Now we come a little closer to home. This is the microcard platform, currently under assembly, integration and test by TAS UK engineers in the cleanroom. Microcarb is a Kinéis microsatellite mission in conjunction with UK Space, with the goal to monitor the fluxes of carbon dioxide at the Earth's surface between the atmosphere and the oceans and vegetation. Here we can see Microcarb, shown without the payload attached and with the sides folded into its flight configuration. We are displaying the full CAD model translated directly from the source step data, and as such every part of the assembly is rendered to a high level of detail. Microcub follows the Kinéis Myriad design in which the 4 side panels are opened during assembly and folded up for flight. The model allows design engineers to check the interior parts will all fit in place correctly. The second model shows the spacecraft in its current configuration in the cleanroom. As well as an aid to fit check, the model in VR can be used to train engineers in the assembly procedures and to get to know the spacecraft they will be building. It has only very recently been possible to show this level of detail in a virtual reality system. These models I have shown today have been rendered with a consumer level PC and 3D graphics card tethered to a headset. This is Microcarb undergoing assembly in the cleanroom as viewed remotely through a HoloLens 2 headset with software provided by Cognitive Spark. The restrictions on travel in the UK during the COVID crisis in 2020 meant that TAS UK were not able to allow our engineers to travel between sites. The problem was solved through the use of augmented remote assistance technology. This allowed an engineer in the cleanroom to make a hands-free call for assistance. The expert at the other end can then see the problem from the same point of view, annotate the headset display, and upload 3D hologram models. Augmented reality not only gives us the ability to view 3D models, but to also view them spatially within a real-world environment. For example, we could use the assembled model of a spacecraft to see where best to place the assembly in the cleanroom. There is also the capability to leverage other functions from cloud computing, such as object recognition to allow tracking of parts during assembly, voice recognition to control the headset operation, and remote rendering to allow multiple headset users to interact with the same model in real time. This demonstration shows some of the potential for engineering training and assistance. This rover model has separate parts that can be interacted with to mount the scientific instruments. Scaling this concept up would allow for valuable training and guided assistance during assembly. It is also possible to create virtual monitors to display windows from a Wi-Fi connected PC. These displays can be interacted with through full finger tracking. Hopefully this presentation has given you a small insight into how we are currently using these technologies and where we may go in the future for industrial operations. Beyond that, we are looking to how they can aid us in the future challenging frontiers of in-orbit servicing, a lunar colony, and exploration of the Martian surface. Thank you for your time.
Thank you, Thales Alenia Space, for joining us today. We'll now be hearing from Dr. Paul Rimmer, an astrochemist and naturalist at the University of Cambridge. He's going to be discussing with us the detection of a 1 millimeter feature in the atmosphere of Venus and the implications if this feature is explained by phosphine. So don't forget to submit your questions for Paul during the Q&A feature. And without further ado, over to Paul.
Hello, my name is Paul Rimmer. I work at University of Cambridge and the MRC Laboratory of Molecular Biology, and I'll be speaking with you about some of the implications of phosphine on Venus. So how about we start? Venus has actually had a really interesting story through history, driven a lot by human imagination, but also by some preliminary scientific conclusions, and might be a sort of cautionary tale about preliminary scientific conclusions, which aren't based on hard data. Sir Arthur Eddington, professor of astronomy at Cambridge at the time, speculated that the surface of Venus could have liquid water, would be relatively temperate, but he did so based on what was known at the time, the distance of Venus from the sun, and some simple calculations of heat transfer. And this speculation inspired a great deal of science fiction, speculating about what life might be there and what life might be like on the surface of the planet closest to us. And it also inspired missions to be sent to explore that surface, largely by Russia and by the United States. And after the first probes were sent, as we see from this, from the title of this New York Times article, Venus says no. What is Venus saying no to? Venus is saying no to life. It turns out the surface is in no way hospitable to any sort of life as we know it, with temperatures surpassing 700 kelvins, hot enough to melt lead and to destroy any of the instruments that have been sent there that were fortunate enough to reach the surface in a matter of minutes. So it's no to life on the surface, but people speculated about the atmosphere. Maybe the atmosphere could have life, and specifically the clouds. Venus has these beautiful clouds. They happen to be at a place with about the same atmospheric pressure as we are experiencing right now, and roughly the same temperatures. So that would seem like a place that was comfortable for life, in a collaboration between a molecular biologist and an astronomer, Harold Morowitz and Carl Sagan. They first put forward this hypothesis and did some speculation about it. It turns out this hypothesis was also based on some ignorance about the composition of the clouds. The cloud composition complicates things for life, as we'll discuss later, but it definitely hasn't ruled out this hypothesis. And if you want to read more about it, I definitely recommend David Grinspoon's 1997 book, still relevant now, Venus Revealed, A New Look Below the Clouds of Our Mysterious Twin Planet. So let's now talk a little bit about phosphorus, since we're building up to phosphine. Phosphorus was seen by one of the Vega balloon missions. That's a picture of what these probes looked like. And it made several measurements of Venus's atmosphere, and it observed phosphorus at about the same abundance as sulfur, about 100 parts per million, which, as we will see, is just an enormous amount, especially to exist in the atmosphere or in the clouds. It also predicted lower atmospheric SO2 drops to 1 part per million, which is inconsistent with more recent remote observations. So these sorts of early probe measurements should be taken with a proper amount of skepticism. They definitely shouldn't be discounted, but they should be treated as being somewhat uncertain and certainly being worth following up. But there's potentially a lot of phosphorus in the atmosphere of Venus. And what form would we expect that to be in? Well, phosphorus can take a lot of different forms of oxidation, which is basically talking about the number of oxygens versus the number of hydrogens that happen to be available to the phosphorus atom. Phosphine itself is listed there, very, very reduced at -3. That's the one phosphorus with the 3 hydrogens. And that is the most stable form deep within the atmosphere of Jupiter, because there's a lot of hydrogen available compared to oxygen, and the temperatures and pressures are right to produce a lot of phosphine. Higher up in Jupiter's atmosphere, you would expect from thermodynamics for that phosphorus to be converted into what's called phosphorus trioxide, which is this sort of polygonal shape of phosphorus and oxygen that is shown there. And actually, that's the particular form that we would expect to be most prevalent near the surface of Venus. It's different than Jupiter because there's a lot less available hydrogen, and the temperatures and pressures don't quite reach the sorts of extremes that they do deep within Jupiter's atmosphere. Higher up in the atmosphere, you would expect most of this to be converted into phosphoric acid. It's also worth noting that phosphine on Earth is observed, and it is of uniquely and exclusively biological origin, either from microbes or from anthropogenic production. And this has been fairly definitively shown for Earth, and this understanding of phosphine as a potential biosignature for other planets has been explored by Clara Souza Silva. Well, in 2020, as you've probably heard, there was this 1 millimeter feature that was observed in the clouds of Venus. And this is a reproduction of this feature. It was observed with 2 different telescopes, the James Clerk Maxwell telescope and ALMA. This 1 millimeter feature that we found is consistent with about 20 parts per billion of phosphine. The signal has been disputed for both ALMA and JCMT by a variety of groups. These analyses disagree with each other, but they do all suggest certain problems with the ALMA calibration. And along with the ALMA team itself, we revisited and improved this calibration, and our reanalysis recovers the 1 millimeter feature that suggests about 1 part per billion phosphine, which to be consistent with the 20 parts per billion seen and maintained by GCMT would suggest that the amount of phosphine in the atmosphere is time varying. Another possible explanation would be mesospheric SO2, SO2 above the clouds. A couple groups have proposed this, but this seems inconsistent with the amount of SO2 that was known to be above the clouds at about that time. However, it also doesn't seem to be consistent with this detailed radiative transfer calculations with the in-cloud phosphine or in-cloud SO2. And so new observations and new analysis really needs to be done to clear up this particular puzzle. From here on out, though, I'm going to assume that the signal of phosphine, that first of all, the signal is phosphine, and that the phosphine is in the clouds. What does it mean for phosphine to exist in the clouds of Venus? Well, let's look at a sort of schematic of what's happening in the atmosphere of Venus, given what we know. So there's carbon dioxide. That's primarily what Venus's atmosphere is made of. It's about 97% that and 3% molecular nitrogen, which I'm not going to talk about because molecular nitrogen is not chemically interesting for our purposes. There's also a lot of SO2, about 150 parts per million SO2. There's also some water vapor, about 30 parts per million, very, very small amount of water vapor present, suggesting that most of the water may have escaped sometime in Venus's history. The CO2 would diffuse up, and it would break apart via photodissociation, ultraviolet photons, which can't penetrate the clouds due to a mysterious ultraviolet absorber, can reach the top of the clouds and break apart the CO2 into carbon monoxide and atomic oxygen. SO2 does the same thing. It gets to the very top and it breaks apart into SO and atomic oxygen. And the atomic oxygen can react with sulfur dioxide, SO2, to form SO3. The water also diffuses up and it can react with the SO3 to form sulfuric acid, which will condense out into sulfuric acid clouds, which is what people primarily think that the clouds are made of. You can ask me later. I have my own speculations about what the clouds might be made of, and some reasons to think that the clouds may have a more diverse chemical composition. But that won't be a topic of this talk. It might be a topic of the discussion later. There's also this particular interesting species, carbonyl sulfide and hydrogen chloride. OCS diffuses upward, where it breaks apart into CO and S. That S will quickly combine with other atomic sulfur, to form S2, S3, S4, S5, S6, S7, and S8. And these are called sulfur allotropes. These also will condense out and they form another constituent of the clouds. Close to the surface, the same sort of thing happens, except because of thermochemistry, the molecules just run into each other. And that breaks the OCS apart into CO, which will also diffuse upward, and S, the atomic sulfur, which will go in and feed again into these sulfur allotropes. The HC, the atomic sulfur near the surface can also react with the hydrochloric acid to form hydrogen sulfide, which can also diffuse up, releases sulfur via photodissociation to form more sulfur allotropes. The same thing can happen with SO. HCl also diffuses up and it does some really interesting stuff with oxygen chemistry in the upper atmosphere, which we can talk about later if you're interested. Geochemistry has to supply a lot of these species and regulate them via unknown surface processes and possible volcanism. And then there's also possibly phosphine in the clouds, which has an unknown origin. There's a bit of a puzzle with the SO2 and H2O, which you can ask me about later as well. How is phosphine destroyed? A variety of ways, but I'm just going to concentrate on really one, which is photodissociation. If you get it high enough above the clouds, it also breaks apart, and it breaks apart rather quickly. And it diffuses. So even if it's below the clouds, it might seem like it would survive a long time. There are other processes, less certain processes that can destroy it below the clouds. But really what will eventually happen, even if those processes didn't destroy the phosphine would be dredged up above the clouds, and then it would be destroyed by photodissociation. This combination of diffusion and photodissociation allows us to estimate a bargain basement flux, the amount of phosphine that has to be produced in the clouds to explain the observations of about 1 million molecules of phosphine per centimeter squared per second. This modest flux may seem easy to produce, but in such an environment, it's very hard to produce any phosphine at all. We looked at a variety of ways to form phosphine. Most of them fall several orders of magnitude, hundreds or thousands of times below this required flux. The one explanation that we know can produce phosphine on Earth, life, seems to be sufficient to explain this sort of flux, but there may be some unknown chemistry going on. The life hypothesis is especially interesting. I would encourage you to ask me about some of the details of this in the Q&A or in Discord later. The next steps of the work are to really confirm or refute the phosphine detection, to explore phosphine and broader Venusian chemistry in the lab, and ultimately, probably to resolve this particular question of life in the clouds of Venus will be to send a balloon or lander to Venus to really find out what sort of chemistry is going on there. I would like to conclude briefly by thanking all of the team that worked on this phosphine detection. I would particularly like to highlight Clara Souza Silva, who first proposed phosphine as a biosignature on exoplanets or on other planets, and Jane Greaves, who found this particular signal, which, though controversial, has definitely reignited a lot of interest in returning to Venus to find out whether there is life in its clouds. And thank you all for listening.
Thank you, Paul, for that talk and for taking the time to join us today. It was really fantastic to hear about the work that you're doing at the moment. So if you're happy to, let's get straight into the Q&A. You mentioned in your talk about sulfuric acid clouds, which are primarily thought of making up the clouds. What is your hypothesis of what the clouds are actually making? Because you had like an alternative idea for that.
Yeah, so it turns out it's very hard to explain the way that sulfur dioxide behaves in the atmosphere of Venus by making the clouds purely out of sulfuric acid, mostly because sulfuric acid requires about equal parts of sulfur dioxide and water vapor. And there's just not enough water vapor in Venus's atmosphere anymore to consume all of the sulfur dioxide. So it seems as though there has to be some sort of hidden source of hydrogen or some other sort of chemistry that needs to be going on that removes the sulfur dioxide into the clouds. And one possibility of this would be various salts that can react with the sulfur dioxide when it goes into the sulfuric acid droplets. What that does is it transforms the sulfuric acid droplets into these sulfite salt droplets, at least some of them, and completely changes their chemistry.
Wow. Yeah.
Yeah.
Fascinating. Yeah, I had no idea that it was so complicated in the atmosphere for Venus.
And I should mention, this is just a hypothesis. No one's actually looked at these cloud droplets directly in any definitive way to know what their composition really is.
And are there any upcoming missions that people should be excited for where this might be uncovered?
There are no missions that have been accepted yet. ESA has a candidate mission, which won't actually go into the clouds, but will look above. Actually, it will be looking at particular spectroscopic windows that allow you to see the surface of Venus. And this will be mostly to look for if volcanism is still active. NASA also has a considered mission, the Da Vinci mission, which would actually go into the clouds, and it might have a special sort of mass spectrometer that would actually be able to distinguish between what the atmosphere is made of and what the cloud droplets or aerosols are made of, so that you could see both together.
We've had a question come in from Ben. Can the phosphine detection be resolved from orbit, or is this an in situ measurement required?
So I think that the remote detection itself could probably be resolved from orbit. It might even be able to be better resolved from something even a little bit below orbit. There's a telescope called SOFIA, which is on an airplane. It's a really amazing feat of engineering. It looks like the telescope's shaking a whole bunch for people who are on the airplane watching it, but it's actually standing completely still. It's the airplane that's moving. When you get to those high altitudes, you can see you have less atmosphere blocking, and so you can see other features a lot more easily. And it may be that you could see phosphine in the clouds with those sorts of spectroscopic windows. But actually determining where the phosphine is really coming from, if it's actually there, or what else is happening in the clouds, would require looking into the clouds themselves.
We've had an awful lot of questions come in, so I'm sure you're going to be very active on the Discord later. One interesting one, just slightly different. Is there possible life on Venus?
I don't think that it can be ruled out. Even going there, I think it'd be very difficult to rule that out. A lot of missions have been sent to Mars, and none of those missions have found any definitive evidence of life. Maybe little signs here and there, but it looks pretty lifeless. But you wouldn't want to say that Mars is definitely lifeless even after going there. Venus is comparatively far less explored. There are a lot of reasons to think that if there is life there, it's probably a different kind of life, just because the clouds are so hostile to life as we know it. But there's no way to rule that in or out without going there, really exploring things, and actually getting a better idea of what it means for something to be alive by exploring different sorts of life here in the lab on Earth.
Yeah, I think that's definitely something which people will have a lot of questions on the Discord, because there are quite a few coming in about life and the life hypothesis. Was there anything else you wanted to add on the life hypothesis? Because we've had a few on that.
I guess that the only other thing that I would say is that Venus isn't the only other place that's worth looking. I do think that it's worth looking in the clouds. The clouds, I think, are intrinsically interesting, but it's also interesting for looking at life in a different environment. But some of the moons of Jupiter and Saturn, Europa, Enceladus, Titan, I think are great places to look for life as we don't know it. Titan especially, because it has these lakes of methane and ethane for which we know life as we know it just cannot work. You need a polar solvent. These are non-polar solvents. If you found life there, first you'd have to come up with a good way to look for it, because you don't exactly know what you're looking for. But once you come up with a good way to look for it, if you found life there, you would really know this is life as we don't know it. There's always the possibility with the clouds of Venus, although this is very, very interesting, that this could still be, even though it's life that's different from ours, it could still be related to ours, and it just learned how to adapt to an acidic environment, because Venus could have been very much like Earth. Even 750 million years ago, it could have been a pale blue dot in the sky. And it just went through this terrible runaway greenhouse, and life migrated into these clouds and just adapted itself to this hostile environment. There's no way to really know that. But for places like Titan, if you found life, you couldn't use that kind of hypothesis. It would have to be something completely different.
Yeah, it certainly seems like it's quite a mystery. And it's great that you mentioned Enceladus before, because so happens that our next talk is on Enceladus. So perhaps perhaps the continue on like the conversation on life will continue into the next talk. So that would be great to see. I guess more of a light-hearted question for people looking to enter where you are currently. What undergraduate degree did you do, and your PhD? How did you get to where you are now?
Sure. So my undergrad was just in physics. I went to graduate school to study string theory, and quickly found out that I wasn't as good at math as I thought that I was. There were people much better at math than I was who couldn't get jobs actually working in string theory. And I wanted to stay in science. And I found out that there was an application for some of the mathematical techniques that I learned that involved chemistry in space, astrochemistry. And so I started working into astrochemistry, and transitioned into atmospheric chemistry, and also now into planetary chemistry and some origins of life stuff, which just means that just because you got a degree in something, it doesn't mean that that's what you have to do. You could end up doing something completely different, like I've ended up doing.
Yeah, it's great. You don't have to just, you can change. You can change your mind and do whatever path suits you. Unfortunately, it looks like we've got time for one more question. So let's go with, can you be certain that phosphine isn't deposited from meteorological events?
Certain is a very strong word. I think that we can be almost certain that it's not being delivered by the standard amount of dust that's being brought in. There's a simple calculation that you can do, assuming that all of the phosphorus in these particles would be converted into phosphine, and assuming very, very high amounts of phosphorus. And it turns out that you're still about 10,000 times too little to explain the signal. However, it may be that in the past 100 years or 1,000 years, a large object struck and broke up in Venus's atmosphere and deposited a lot of phosphine that's just been living below the clouds and is slowly being raised up higher into the atmosphere. That might be a source. That can't be completely ruled out, or at least not ruled out with as great a confidence as this sort of background amount which is being provided.
Thank you so much for elaborating on that. And unfortunately, that is all we've got time for today. But thank you so much for joining us, Paul. It's been really nice chatting to you. And if anyone does have any more questions for Paul, or would like to discuss some of the points you raised in your talk, because there were a couple of things you're like, oh, I'd like to discuss this later, just head over to the Discord. Paul, I believe you said you'd be there for about an hour?
Yes.
Perfect. So if anyone's interested, head over to the Discord and Paul will be there to answer any questions. So next on today's program, we have Grace Richards, a PhD student at the Open University. She is working on developing new protocols and techniques to analyse icy moon surfaces. Today she'll be talking about Enceladus and unlocking the secrets of its surface. Please submit any questions you have for Grace in the Q&A function. So take it away, Grace.
Hi everyone, thank you for taking the time to come to my talk. I'm Grace and I'm a PhD student as part of the astrobiology group at the Open University, and my research focuses on Enceladus. So I hope you're enjoying the talk so far. I came to the conference as a master's student in 2019, so it's really nice to be here speaking today. So I'll be talking about why Enceladus is one of the most interesting places in our solar system and what kind of information we can get from looking at its surface. I'll be giving an overview of the structure of the satellite and the space environment which it's in, and then I'll show you about what both the composition and the physical properties of the surface can tell us about surface processes. So at the end, I'll also be talking a little bit about my PhD research. Okay, so Enceladus is an icy moon which orbits around Saturn, and it's the 6th largest moon and only around 500 kilometres in diameter, so roughly the size of France. And although it's pretty small, it's geologically active, and on the left here you can see the expected interior structure. So it's expected to have a silica interior with hydrothermal activity, which allows for chemical reactions between the liquid water ocean and the rock of the interior. And the evidence for both liquid water and hydrothermal activity has led to Enceladus getting a lot of interest from the astrobiology community, because on Earth life has evolved where there's liquid water, an energy source and bioessential elements, and Enceladus satisfies all three of these requirements. Okay, so the water ocean is covered by a thick icy crust, and in the South Pole there are these huge fractures called the tiger stripes, and you can see these on the right now. So they're around 130 kilometres long, around 2 kilometres across and 500 metres deep. And they're host to around 100 jets which vent out icy material from the ocean thousands of kilometres into space. So the majority of plume material actually falls back onto the surface, and this is around 99% of the material. And this mainly happens around the tiger stripes. But it can also travel further afield, as lighter material follow a less ballistic motion and provide a global coating of kind of ocean material across the whole of the satellite, even in the North Pole. And in this way, looking at the surface, composition and features can give us a good indication of processes and the composition of what is beneath the surface. So the rest of this material goes on to feed Saturn's E-ring, which Enceladus orbits within. And the E-ring is the second outermost planetary ring of Saturn and is composed mainly of icy grains and silicates. As Enceladus orbits within this structure, these grains can be redistributed on the surface of Enceladus. So this process kind of recycles plume material through the E-ring. E-ring grain impacts are basically micrometeoroid impacts because the majority of the grains are less than 10 microns in diameter, and quite a few of the grains are on the nanometer scale, so they're really small. And in this way, these E-ring grains can make up some of the surface composition. Because the grains originate from the plumes, and therefore the ocean of Enceladus, their composition could be assumed to be similar to the plume material, and it is, although there is quite a bit of silicate material there as well. So the E-ring in Enceladus is also embedded in Saturn's magnetosphere, which is formed of trapped plasma and energetic particles. And these charged particles weather the Saturnian satellite surfaces, as well as E-ring grains, and so the surfaces are continually being bombarded by around kilo-electron-volt ions and mega-electron-volt electrons. And this can drive chemical reactions and species creation, as well as altering the physical properties of the ice, so like the grain size. So why can't we just sample the plumes or go to the ocean? So the ice is expected to be thinnest in the South Polar region, where it's around 5 kilometres thick. However, even on Earth, the technology doesn't yet exist to penetrate ice this thick. So it makes it unlikely that we'd be able to reach the depths required to reach the ocean, even in space. And the Cassini mission did sample the plumes. However, this material is travelling really fast, so impacts detectors at high velocities and fragments the particles. So although this has given us a lot of insight into plume composition, the surface isn't a moving target, and you can also target locations of interest. So you can go to the South Polar region if there's a mission going there. So as well as that, it can also give us a lot of information about other processes which are affecting the surface. So for example, space weathering. So moving on to what we'd actually expect to find, all our information of the surface comes mainly from infrared observations and also UV measurements. But it's important to note here that the only firmly detected surface species are water and carbon dioxide. All the rest are tentative detections. So the majority of the surface is composed of water ice, and this is why the surface is so reflective. It's one of the most reflective bodies in our solar system, and this is being constantly replenished through the ocean material, which is also liquid water. There is also a lot of CO2 ice, well, when I say a lot, up to around 5% on the surface, and this can be found either as free ice or complexed with other materials like the water ice. And this is expected to be present because it was either formed in the ocean and then has been ejected by the plumes back onto the surface, or is produced by irradiation of organics on the surface. So there's evidence for light organics on the surface, but then some of the spectral signatures also match up with hydrogen peroxide and methanol, although this is quite disputed. But these all show different mechanisms of being there. So hydrogen peroxide would indicate a more intense radiation environment, similar to Europa, which is one of the icy moons of Jupiter, and methanol could be derived from methane in the plumes. Ammonia has also been detected tentatively by both ground-based telescopes and Cassini data, and would need to be constantly replenished on the surface because it's not very stable and would be potentially destroyed by irradiation from the magnetosphere. There's also potentially salts there, which could derive from the plumes, but also tholins, which again are long-chained organic molecules, and these are formed by radiolysis. So, as well as that, the presence of iron on the surface could also be derived from micrometeoroid impacts. So you can see here that surface composition can give us a good indication as to what kind of processes affect the surface, as they're derived from different sources. So something else I'd like to talk about is how the physical properties of the ice and what the physical properties of the ice can tell us about what's happening on the surface. So on this slide you can see the surface of Enceladus made up using data from the visible and infrared mapping spectrometer and the imaging science subsystem, which were on board Cassini. So ISS is an instrument on board Cassini, not the International Space Station. So both of these instruments used visible and infrared measurements, and VIMS got spectral cubes of the surface and ISS got actual images. So these really beautiful overlays of the data show water ice on the surface, and the redder parts here indicate areas of higher crystallinity. So water ice on the surface can either be crystalline or amorphous, and you can differentiate between the two because they show distinct spectral characteristics. Amorphous ice is produced by radiative processing or rapid condensation of water vapour onto an icy surface, so this is more likely to show older surface ages or gaseous plume mechanisms. Crystalline ice is more likely to show ice grain surface deposition or younger surface ages. So you can immediately see that around the tiger stripes, the ice is more crystalline, denoting younger surface ages and icy grain deposition. What you can also see in this area is the clear boundaries between the red and the blue parts of the image. So this is really interesting because it indicates that variations in the spectra in these regions aren't due to plume deposition, but actually due to geological processes. So this is also potentially evident in the mid-latitudes. So if we just move up here, okay, so if we move on to the leading side of the satellite, so this is the side which faces the direction of the orbit, this red area shows an increased crystallinity and matches up really well with this kind of smooth tectonic region which has been previously defined. And this implies that freshwater ices have been exposed recently on geological timescales. And it's also important in locating seafloor hotspot regions outside of the South Polar region, so the Tiger Stripes. So compared to around the poles, seafloor hotspots in the equatorial regions are expected to be much more chaotic in nature, so they only remain stable for a few million years. So the red area here shows that it's likely that there's been recent seafloor activity, maybe during a period of higher orbital eccentricity, which has led to increased tidal dissipation in the core. So more pull on the satellite has generated more heat. So the sizes of ice grains can also give us a lot of information about the satellite. If we go back to the Tiger Stripes, the grain sizes in this region are expected to be much bigger, as larger plume material is more likely to follow a ballistic motion and therefore be deposited around the vents. Smaller particles are also more likely to be distributed around older regions, which has undergone heavy cratering. So here you can see some of the oldest regions of the satellite in the northern hemisphere. So in this way, grain size and crystallinity can be used to estimate surface ages and determine geological features. So it's also important to get a bit of a clearer picture about which processes match up to what kinds of composition, and this is where my research comes in. So my PhD focuses on how we can use mass spectrometry to determine the composition of Enceladus's surface. Unfortunately, because of COVID, my lab time has been extremely limited and I've only just started to be able to get into the lab, which is exciting because I've been learning all the different equipment and setting it all up ready for my experiments, but I am fairly behind in terms of getting any results. So I just wanted to talk to you through what I'm planning to be doing and also what I'm in the process of starting to do. So I will be aiming to get a range of potential compositions that represent Enceladus's surface, and this is based on what we already know about the surface and the plume composition. So I'll be getting a nice range of potential compositions, and these will all be grown in situ. So I'm using a vacuum chamber to grow them, and this is being cooled down using liquid nitrogen to temperatures down to minus 169 degrees Celsius. So around the Tiger Stripes, the temperatures are around minus 95 degrees Celsius, which is pretty hot compared to the rest of the satellite, because the average surface temperature is around minus 198. So I'm working at temperatures just a bit lower than the Tiger Stripes. And this is the stage that I'm currently at with my project. After I have my ices, I'll be optimizing analysis techniques using mainly mass spectrometry based instrumentation. Initially, I'll be using GCMS, which is the gold standard for analysing both the isotopic and chemical composition of samples, and it has also been integral to previous spacecraft payloads. So this is going to be to ensure that my ices are actually representative, and what I'm putting in the vacuum chamber is what I'm getting out. So I'll then be moving on to working with a miniature ion trap mass spectrometer, and this will be used within the chamber in order to try and replicate kind of spacecraft conditions and in situ analysis. So then the part of my project which I'm most looking forward to is right at the end, and I'm going to be investigating different space weathering techniques and processes. So my aim here is to focus on micrometeoroid impacts or E-ring grain deposition and try and see how this affects the physical and compositional properties of my ices. If I have time, I'll be moving on to doing some electron beaming experiments to try and replicate the effects of the magnetosphere. I can then try to get together kind of database of before and afters in order to match up which space weathering process does what and how it affects the composition, and making this really specific to Enceladus. So in this way, I'm trying to develop a more complete picture of surface processes. Okay, coming to the end of my presentation now, I hope that I've been able to show you that even though it's really small, Enceladus is one of the most interesting places in our solar system. So by looking at both the composition and physical properties of the ice on the surface, we can find out a lot about what is actually happening both on the surface of the satellite, beneath the surface, and also about the space environment which Enceladus is in. So I hope you've enjoyed learning about the Enceladus system, and I'll leave you with this diagram which shows us some of the processes which actually affect the surface. And I'm happy to take any questions.
Fantastic, thank you, Grace. Enceladus really does seem like such a fascinating area of research with so much intrigue surrounding it. So I guess to kickstart us, how likely is it that there is life on Enceladus, or at least in the near future?
I mean, I would not say that it is that likely, to be quite honest. I mean, but we just don't know, do we? Because we haven't really seen beneath the ocean at all. We don't know what's going on down there. There are, you know, like, as I said, on Earth, you look to hydrothermal vents and there's like thriving biological communities. We literally don't know. I guess something that I've been a bit concerned about with my PhD research is you take a tiny bit of ice and look at what's in there, and then you try to infer what's going on beneath the surface. It does seem kind of unlikely, you know what I mean, that you're going to get a lot of information, but you look at other space missions and there's so much you can learn just from in situ sampling. Like, I don't know. I feel like it's very much an open door, you know?
Yeah, you never can tell, especially when it is so hard to do missions, which leads us on to another great question that someone's asked. Are there any upcoming missions to Enceladus or Jupiter that we can be excited for?
So there's not any to the Saturnian system planned, but there is the upcoming ESA mission JUICE, which is going to go to the Jupiter system and like have a look at the icy moons there, including Europa. And then also NASA has Europa Clipper planned, which is also going to Jupiter, and that is also going to lead on like a reconnaissance mission, which will lead on to Europa Lander, hopefully, which should be launched. Well, it's hoped to be launched about 3 years later, I think, after Clipper's launch. So there's a lot going on with Jupiter, and then that's exciting for icy moons, but then not much planned for Saturn, but hopefully in the future there will be.
Oh, it's a shame Saturn's being a bit neglected at the moment, but fingers crossed in the near future it will be okay. One question that I had watching the talk actually was, what causes the crystallinity in the tiger stripes, and why are they that beautiful red colour?
So on the video that I showed, the red is it's not the actual like colour of the ice. It's like it's all from infrared measurements. So the ice is that crystalline because it can be like icy grain deposition models. So icy grains that get ejected from the plumes, which then go onto the surface and pack to keep the ice crystalline, right? And that's pretty much why it is, I guess, as well. Like it's quite fresh. It hasn't undergone any like radiative processing or like very minimal radiative processing. So it's still pretty like nice and regular ice.
We've had another question on tiger stripes. Tom has asked, do we have any idea why the tiger stripes are so localized and not at the North Pole as well?
So they're so localized because once you get one kind of fracture in the ice, that exerts more tension around that area. So it's more likely that the stripes formed in parallel. So that's why they're so kind of like regular, I would say, around the South Poles. But I guess they've kind of formed through heat being dissipated and then fracturing the ice. There's been a little bit of work about cratering and potentially that leading to more fractures. But I guess it depends on the orbital dynamics of the moon as well. So as it orbits, there's going to be areas of greater tension on the satellite, and that can lead to the fractures.
Okay, wow, yeah. We've got a question from Natasha. Would silicon-used life forms be more likely due to the core composition, or would it be more carbon due to methane on the surface?
Okay, so I'm not 100% on this question. I guess if you're thinking about silicon-based life, like the thing with silicon is it's very inert. So it seems, I mean, from my perspective, it seems less likely that silicon-based life would really work. I guess all we know is carbon-based life. So we're very much working with a sample size of 1 for astrobiology research. But I mean, there are carbon compounds on Enceladus. Like the silicate is mainly found, you know, in the interior of the satellite and also like in the E-ring grains. But yeah, that's an interesting question. It goes kind of beyond like looking at the like tiny little samples of the ice and then like thinking about, okay, well, what kind of life would there be?
Yeah, no, for sure. I mean, it keeps circling back to this, is there life? That seems to be the main topic that really intrigues people, people at the moment. We've had a question coming in about how similar is the environment on Europa to Enceladus, and is your work valid for Europa as well?
Yeah, so Europa is quite a bit bigger than Enceladus. It's also got to deal with like Jupiter's crazy gravity. There's also a lot more, there's the surface of Europa, it's called like the chaos terrain, where there's loads and loads of fractures, which you can see, and there's expected to be plumes there as well, which have more recently been detected. There's a lot more hydrogen peroxide on the surface, and that's formed because of the radiation environment of Jupiter. So Jupiter has a lot more intense radiation than Enceladus, which is not necessarily the best thing if you're looking for life. But there are a lot more, I don't know, there's a lot more surface area, there's a lot more fractions as far as
it's quite different.
Yeah, it is quite different, but they are similar. Like there's oceans, there's an icy crust, like they're mainly water ice. Yeah.
Okay. Have you looked into many of the other icy moons? Like how did you fall into looking into Enceladus in particular?
So I'm not too sure. I was always like very drawn to Enceladus. It's so small, and I'm kind of like I always kind of think about how it's so small, but it's one like geologically active. I think that's, I don't know, really cool that it's managed to have all the plumes and everything, even though it's so tiny. I guess as well, it's further away, and I kind of like that it's so far away and kind of like pushes our limits of what we think habitability is. So you've got like the habitable zone, and then you go further and further out in the outer solar system, and you're still finding liquid water. So that's something that I'm quite drawn to. But yeah.
So there's a certain je ne sais quoi about Enceladus that drew you in.
Yeah. Oh, I had a point then, but I lost it.
It's okay. Just we've probably only got time for one more question. So just to wrap things up quite nicely, what did you do for your undergraduate, and what advice do you have for people looking to do a PhD but not quite sure what to do it in?
Okay. So for my undergrad, I did physics, and I was at Edinburgh doing that, and I also did the MPhys program there. So I did an integrated master's, and then towards the end of my degree, I started focusing more on astrophysics and did some astrobiology projects, both in summer research projects and also for my master's project. And what I'd say about a PhD, for me, very much, it was something, you know, you're doing it for a long period of time and it's the only thing that you're focusing on. You need to be enthusiastic about it and really enjoy what you're looking at, and also really look at your supervisory team as well, and, you know, who you want to work with. But also don't give up if you don't get your first choice, or like you get a few rejections. Like I got quite a few rejections, and you just got to persevere a little bit and also find the right program.
Excellent advice. Yeah, it's all about finding the program that suits you and just pushing through, because yeah, PhDs are hard as far as I'm aware. I haven't done one. Yeah. But thank you so much for joining us, Grace. Unfortunately, I think that's all we've got time for, but it's been a pleasure chatting to you. And you did say that you're going to be on the Discord later, so if anyone has any more questions for Grace, feel free to head over to the UK SEDS Discord server I believe the link to that is along the banner at the bottom of the screen. So head over there. Grace will be there to answer any questions that you have. We're now going to be taking a short break. So join us back here in 5 minutes for our keynote talk from Professor Yuichi Tsuda, the project manager for Hayabusa 2. He will be discussing the asteroid sample collection mission from the Japan Aerospace Exploration Agency. Hopefully you've enjoyed this morning's program, and we'll see you after the break.
Hello, everyone. Welcome back after that short break and some amazing talks and panel discussions this morning. Right, I will just remind you of the hashtag that I missed this morning in the opening. That's NSSC selfie, and I believe we're now going to post a link for that in the chat. So hopefully you can send a selfie if you want to. If you haven't done so already, we've had some great submissions already, so hopefully you can get some more. Right, on with our keynote. We are really excited for this keynote today. We have for you Professor Yuichi Tsuda, who is a professor in the Institute of Space and Astronautical Science at the Japan Aerospace Exploration Agency. He is the project manager for the Hayabusa 2 asteroid sample return mission. In 2000 to 2003, he was the student project manager of the world's first CubeSat project at the University of Tokyo. In 2009 to 2013, Yuichi was also the deputy project manager of Icarus, the world's first deep space solar sail mission. He then took the role of project engineer of Hayabusa 2 from 2010 to 2015 and became the project manager in 2015, succeeding in the sample return from the asteroid late last year. He's going to tell us all about this mission and what the team went through, and he'll be answering some questions here straight after the talk and then also be on Discord after that. So I will now hand over to him.
Okay, so thank you for inviting me to this exciting event. My name is Yuichi Tsuda from Japan Aerospace Exploration Agency. Today I am talking from Japan, and I'm very happy to talk to young people in the UK and Europe. I am leading the space mission called Hayabusa 2 as the project manager. Hayabusa 2 is a Japanese asteroid sample return mission to visit an unexplored asteroid, Ryugu. Hayabusa 2 successfully landed twice on Ryugu, created a big artificial crater, and deployed as many as 4 mobile robots. All in success, Hayabusa 2 returned Earth last December. I would like to talk about Hayabusa 2, how Hayabusa 2 was operated, and what we achieved in the Hayabusa 2 mission. So this is the mission scenario of Hayabusa 2. It's a sample return mission to a C-type asteroid, Ryugu. C here means the carbon rich. And the mission is a 52 billion kilometer interplanetary journey. And it was launched December 3rd, 2014. And after 3.5 years of the interplanetary flight, it arrived at the Ryugu on June 27th, 2018. And after that, Hayabusa 2 basically flying around the asteroid, fly over the asteroid, and attempted many challenging operations such as rover deployments and 2 touchdowns and a kinetic impacting operation to make a crater on the surface of an asteroid. And then after 1.5 years of stay there, then the spacecraft left Ryugu on November 13, 2018. And after 1 year of the interplanetary flight, the spacecraft successfully returned to the Earth last December 6, 2020. So before talking about the mission itself, I would like to briefly talk about why do we like asteroids, or why the Hayabusa 2 mission so important. In this picture, you can see the sun in the center, and the Earth moving around the sun once per year. Actually, it's the definition of the 1 year, you know. So you also have Mercury, Venus, and Mars, Jupiter, Saturn, Uranus, Neptune, and so on beyond this screen. So now I will add small bodies discovered by Earth-based telescopes in this chart. How many small bodies do you think we have in the solar system? Like this. So green dots, red dots, all these dots are the asteroids or comets. Again, how many do you think? As of 2020, it's almost reaching 1 million. And indeed, it's increasing due to the evolving performance of telescopes and also the technique to detect the dark and faint objects. So now you can understand that the solar system is not a sparse environment. It's very congested space full of small bodies. Therefore, it's important to study about small bodies to fully understand about the history and the truth of the solar system. Then the Ryugu is orbiting around the sun like this. So it's an elliptical orbit between the Earth and Mars, and its period is about 1.4 years, a bit longer than the Earth. And in addition, among as many as 1 million small bodies, Ryugu is a special asteroid in the sense that it is estimated to have a rich carbon and water. Carbon and water are, the two essential ingredients of life on Earth. So if you look the universe through this special asteroid Ryugu, then you may be able to understand not only about the Ryugu itself, but also about the history of the solar system and the origin of water and life on Earth. And bringing the sample of Ryugu back to Earth is the most effective way to realize this scientific goal. By the way, I am an engineer, so I prefer talking about in spacecraft to the asteroid science. For engineers like me, it's so exciting to make the spacecraft which can go to the other planets and come back to Earth, isn't it? So Hayabusa 2 looks like this. It's a 600 kilogram spacecraft with 6 meters span tip to tip. It's a relatively lightweight spacecraft in spite of very large orbital maneuver capability. As many as 15 scientific instruments are aboard the spacecraft, like cameras and robots and sampling system and the kinetic impact system and so on. And this is the orbital design of Hayabusa 2 from Earth to Ryugu. The key to realize our round trip mission is ion engine, which is here. It's a very high efficiency propulsion system, 10 times more efficient than the ordinary chemical rocket engine. By making full use of it, Hayabusa 2 can reach Ryugu and then return to Earth despite very compact spacecraft body with variety of scientific instruments. And Hayabusa 2 arrived at the Ryugu on June 27, 2018, already more than 2 years from now. The appearance of Ryugu was surprising. How do you express this shape in your country? We Japanese said it's like a top shape, or two champagne glasses, or if you know well about stone, it looks like fluorite, or Death Star of Star Wars movie. The size of asteroid is only 900 meters, so it's a very small asteroid, and its gravity is very, very small. And it's rotating at the period of about 7.6 hours, about 3 times faster than the Earth. The biggest headache for us was the Ryugu was covered with full of boulders all over the surface, and we could not find any safe place to land. Anyway, we have to do the exploration. The first thing we did was deploying 3 rovers out of 4 to the surface. The first 2 are called Minerva 2-1, developed by JAXA. The second one was called Mascot, which was developed by German and French partners. And all these successfully landed on Ryugu and did autonomous mobile activity. And like this, so they can hop and wandering around the surface of the asteroid autonomously. I think this is the world's first successful mobile activities of surface exploration robots on small bodies. So in the meantime, we were struggling to find a way to land on the bumpy asteroid. Our original landing accuracy specification was 50 meters, but we found that we had to improve down to 3-meter landing accuracy to achieve the safe landing. We did many additional survey of the asteroid surface, and also many tests and simulations to improve our landing accuracy performance. The key to the final solution was here, the target marker. The target marker is a 10-centimeter reflective ball here, and the spacecraft can detect this as the bright spot by the onboard camera autonomously. So the strategy that we built up to make full use of this target marker. First, we drop the target marker on the real surface like this. And then, second, find a safe place near the drop the target marker. And then finally, land to the ground using this target marker as a visual navigation marker for the spacecraft. So this is the computer graphics movie of the landing sequence that we built up specifically for review. So spacecraft first descend down to 8.5 meter and find the target marker. And while tracing this target marker by the camera, spacecraft moves horizontally to the right above the landing site, like this. And then establish the final descent altitude, like this. And then finally make a free fall from 8.5 meter to the ground, like this, to target to the landing site, the safe place. And the landing itself is very short time. So after detecting the touchdown, the projectile is ejected from the root of the sampler horn, and the reflected fragments are collected at the root of the sampler horn and transported to the reentry capsule. The spacecraft immediately ascend to the higher altitude. And this was actually conducted on the February 22nd, 2019, and this was the final descent sequence observed from the onboard camera. And you can see the beautiful touch and go sequence successfully completed. And please think of the fact that this was done 300 million kilometers away from Earth autonomously. And the resulting landing accuracy was this time only 1 meter. So the next thing we did was a novel experiment called kinetic impact. This is to make an artificial crater. Soon, this one called impactor will explode. Before that, the spacecraft has to escape to the backside of the asteroid to avoid the explosion debris. And waiting about 40 minutes for the complete escape. Then the impactor is activated and make a hole on the surface like this. And the process of cratering is something you don't want to miss. But the spacecraft itself cannot observe it because it's escaping. So a very small deployable camera is separated just before the escape is completed to observe the impact process at the dangerous place, like this, and send the movie data to the mother spacecraft before it is killed by the debris. And it was very challenging engineering experiment, but we succeeded in it. You can see the crater forming process in the perfect manner. And HALEPSA-2 could even observe the impact point before and after the impact, and found that 14.5 meter diameter crater was generated. The observation of the impact process and the crater terrain were already valuable science, but the most exciting science should be to get the subsurface material exposed by the kinetic impact. Thus, we decided to land here to get the subsurface samples ejected from and accumulated from the impact event. Then the second touchdown was conducted on July 11th, 2019, and there was perfectly success. So please just look at the beautiful landing. This time it's more beautiful than the first touchdown because the landing accuracy this time was as small as 60 centimeter. Okay, then after all these successes, Hyapsatu left Ryugu. Using ion engine again, Hyapsatu approached the Earth. In the landing area, Uluru Desert in Australia, about 100 people were deployed to wait for the Earth's re-entry. And please watch the short video on the recovery operation. Okay, thank you for watching. And after bringing the capsule back to Japan, we opened it and found 5.4 gram of Ryugu samples there. Our mission criteria was 0.1 gram. So the 5.4 gram is far more samples than expected. And we have two chambers, separated chambers for first touchdown and second touchdown. So we could retrieve the samples from two different sites separately. It's a scientifically important point. And the spacecraft itself is continuing its space flight. And after releasing the capsule, Hyapsatu diverted from the reentry orbit and escaped to the interplanetary orbit again. Hyapsatu mission is then transferred to extended mission activity. And Hyapsatu still has 50% ion engine fuel left aboard the spacecraft. And so we are aiming at flyby the new asteroid 2001 CC21 in 2026, and the rendezvous to a new asteroid 1998 KY26 in 2031. These are scientifically very interesting asteroids, and we hope that the spacecraft would be flying for another 10 years or so to complete these new missions. And finally, this project is a very big team with many domestic and international members. We faced difficulties on Ryugu, and without our good teamwork, we could not have overcome any one of them. the spacecraft exploration is such a difficult attempt, and at the same time worth doing from the viewpoints of evolutions of science, technology, and human society. So with that, I would like to conclude my talk. Thank you very much for your attention.
Wow. Thank you, Professor Tsuda. That was an incredible mission and an incredible talk. And we're so grateful that you could share this with us. And Professor now joins us for a live Q&A. And it's amazing to see so many questions coming through. And we're not going to sadly be able to get through all of them right now, but he will be on Discord straight after this, where you can ask more questions. So let me just kick off with a great question that's come through. And that's, out of the nearly 1 million asteroids in the solar system, why did you choose this one in particular?
Okay, yeah, that's thank you for good question. And there are mainly two reasons. One is more from the engineering viewpoint. So even with our ion engine system or spacecraft performance or technology, we cannot go far beyond the Mars for the round trip mission. We can do the one-way mission, but as for the round trip mission, we have to go to a planet and go back to the Earth. So for that, the space between Earth to Mars is the maximum that we can do. So we had to find the appropriate asteroids within that region. That's the reason number one. And reason number two is that even with that, there are plenty asteroids, like more than 10,000. But with the we wanted to target or aimed at the carbon-rich asteroid because the carbon is with the carbon we can do a very precious science, like the origin of the life on Earth or something like that. So but in that space between the Earth and Mars, most of the asteroids are made of rock, just a rock. But some of the asteroids are carbon-rich asteroids, and we tried to find a good carbon-rich asteroids from that region, and we could only find 3 candidates. And out of 3, we tried to choose the best one. That's the asteroid we do.
Yeah. Oh wow. Sounds like there's a lot of work going into selecting that in the first place before you can even think about how to get there. So what does this mission really mean for the future? What have we learned that we can apply to similar missions in the future? And what can we actually gain from a successful mission like you had?
Okay, so it's so how can I answer? Yeah, so the Hayabusa 2, Hayabusa 1 and Hayabusa 2, those two are the only successful interplanetary round-trip mission so far done by humankind. And there are some other missions which are trying to do the round-trip mission in near future, like NASA's Osiris Rex. But so far there are only 2. So, but from like many science fiction movies says that there are more and more spaceships that are going to other planets and coming back to Earth, a round trip mission, manned round trip mission. But we only have done such round trip mission only to the asteroids so far. So we haven't done the Mars round trip mission, Jupiter Mars round trip mission, just because of the engineering technical limitation. But in near future, we have to do that,
Yeah.
So this I think this is the very good first step for mankind to realize the kind of the very sophisticated interplanetary flight. I think that's this is the first step for that.
Amazing. I'm sure everyone's really excited to see what comes next. Huge congratulations on the mission. Unfortunately, we are now out of time on this live stream for the Q&A, but as I said, the professor will be over on the Discord. Carrying on this stream now, we have some quick fire talks on all sorts of in-space manufacturing, kicked off really by Mike Curtis-Rouse, who is the head of in-orbit manufacturing and all sorts of in-space manufacturing assembly at the Satellite Applications Catapult. He'll be setting the scene for this stream. And over on stream 2, we have a Space Careers workshop given by Ivona. So thank you very much again to the professor, and I hope that you can go and talk to him on the Discord.
Yeah, my pleasure. Thank you very much.
Thank you.
Hi there. My name is Mike Curtis-Rouse. I'm the head of manufacturing for space at the Satellite Applications Catapult, and I'm really pleased to be able to give this presentation at the SEDS 2021 conference on the commercialization of space, the new frontier. So it's been a pretty exciting year so far. I think it's a really good place to start in terms of talking about where we're going and how we're getting there. So Virgin Orbit having a successful launch, doing an air launch of a rocket, really is an indication of where we're going. And that indication of where we're going is really where we're going to start building this effectively, this growth commercialization of space. So in the past, conventional rockets have basically been the way we've put things into space. Rockets having many stages, typically being complicated, even potentially as they become more reusable, they still remain a relatively expensive way to put things into space. And in order to commercialize space, we've got to be able to get things into space cost effectively. So this whole new paradigm shift in terms of air launch vehicles, small launchers, different launch technologies is enabling us to put things into space at far lower costs than ever before. And fundamentally, if we're going to do things in space, we need to be able to get to space cost effectively. However, are we talking about effectively going somewhere, perhaps for those of you who might admire Star Trek, if not Star Wars, and thinking about effectively big spaceports floating around the Earth, massive capabilities? Is this something that we're likely to see by 2150, 2200, 2300? Actually, in putting together this presentation, I've realized that we're probably actually talking about being able to see constructions of this size probably in the next 100 years. Not perhaps 2150, but certainly at the same time, we're not talking 2300 or 2400. We're talking about something that perhaps for some people in this room, some people listening to this presentation around the world, wherever you might be, you may well be able to see or be involved indeed in spaceports being constructed on orbit to build far larger spacecraft and other products. However, if we come back down to Earth, what is the situation? What's going on Earth? Reality is that, again, going back to Virgin, Spaceport America, a joint partnership between Virgin and Foster and Partners, was projected to look something like this. And for most of us, we could look at this and say, it looks pretty attractive, but the probability of this being real is fairly slim. However, this was the projection, and today, or effectively last year in 2020, and certainly I suspect still today in 2021, it looks pretty much like this. So the difference between those two sites is actually very, very small. So we are beginning to see actual commercial space begin to manifest. However, let's come back a little bit more local to the UK. So this is the vision for one of the 7 spaceports in the UK, Sutherland Spaceport, up near Dunray at the tip of Scotland. This is the vision. Today, this is the reality. So we could argue we've got somewhere to go before we actually start building something which looks a little bit like Spaceport America. But that said, it's not stopping the spaceports from around the world popping up effectively across the UK and elsewhere in the world. Today, there are something in the region of 30 to 40 different sites across the world looking to be spaceports. And within the UK itself, we have 7 locations which are aspiring to be spaceports. For the most part, those in Scotland tend to be vertical launch, and those, with the exception of Prestwick elsewhere in the UK, tend to be horizontal launch. And there's a good reason there for that, clearly. If you're going to launch something vertical, you're going to be dropping stages, therefore you want to drop those stages over water, not land. And likewise, if you're taking off from a horizontal perspective, you're less likely to be dropping stages, therefore it's easier to have a spaceport in Newquay and Llanbedr and elsewhere. But why do we need spaceports? Well, spaceports are a good way of driving the investment in new space, because that investment in new space is growing It's getting bigger. It's coming from a whole variety of new locations, a whole variety of new organizations. And I just put on the screen, for example, here, just some of these interesting areas where we're seeing this investment come from. So ISAR Aerospace, a German company, small company focused on rockets, small rockets, as everyone wants to build these days, received close to 15 million euros from an early VC fund. Meanwhile, Spire, who are in the process of going public as we speak, received close to 17 million euros led by Scottish Enterprise. And at the bottom, Swiss 212, who make RF surfaces for antennas, but space-based, received another 17 million from Swisscom Ventures. So we're seeing investment into a variety of companies where in the past, business people, organizations, venture capital funds, rainbow seed funds, angel investors would have looked at organizations like this and said, you know what, it's probably too risky and we can't see a market. But suddenly there is a market today. It's small sats, it's launch, it's antennas, it's laser comms, and it's more than that. It's what can we do in space? And we're already seeing real utilization of the in-orbit servicing and manufacturing services. So this was last year with the Northrop Grumman Mission Extension Vehicle, MEV-1, docking and raising an Intelsat to a high orbit. The satellite being effectively raised had run out of fuel. The MEV transfer vehicle basically docked with it and boosted it to a higher orbit, giving it utilization again. And this year we'll see another mission extension vehicle, MEV-2, unsurprisingly, doing something very similar. So we're already seeing that IOSM services are coming of age, going beyond scientific purposes and creating real commercial opportunities. At the same time, we're seeing bigger ambitions and bigger opportunities. I'll touch on this slightly later, but the ambitions are growing in terms of what can we do with commercial space. And orbital solar, for example, is one of these things. Now, what's driving this? Well, fundamentally, let's keep the maths out of this where we can. But basically, a lot of this is being driven by the desire to build rockets. And the perception is that rockets are fairly simple. And in reality, they really are. Take the maths out of it, and ultimately, all you need to do fundamentally is move fast enough and high enough, and you're in orbit. Now, clearly, you're going to have to keep on moving relatively fast in order to stay in orbit. But that's the basics of it. What does that mean? Well, that means in conjunction with a variety of new technology like additive manufacturing or more conventionally known as 3D printing, in theory, if you think you can build a rocket, if you've got a wallet which is filled with euros, dollars or pounds, which allows you to spend, and you can get access to 3D printing technology, then in theory, most people think they can build a rocket. Now, building rockets is fundamentally, we could argue, fairly simple, but equally, it's fairly complex at the same time. And everyone from the likes of SpaceX to Mitsubishi Heavy Industries to those building model rockets in the Utah and other deserts have learned that rockets don't always go to plan. But that doesn't stop people. What I find fascinating is 10 years ago, there were about 12 companies building launch vehicles. However, today, there's 280, actually wrong. That's changed in the last day. As of today, there were 292 launch vehicle companies aspiring to build rockets, balloons, space planes, catapults, and a whole variety of other platforms to get into orbit. And what does this mean is, well, this means there's a lot of drive. There's a potential lot of capability, and there's a lot of potential for people being able to put things into space. And if we can put things into space, then we can do more things in space. Now, I don't want to wax lyrical about too many companies out there. There are many, and many of you in this conference will probably be part of them. You'll know people who have started companies up, will be involved in them, or will be aspiring to start your own. One of the ones I would like to mention is Protolaunch. Protolaunch spun out of one of our facilities that the Catapult incubates at the Westcott Venture Park in Buckinghamshire. They're a small company out from the University of Cambridge, and they're aspiring to build a new type of rocket engine, which I show you here. It's interesting. I won't steal their IP by telling you exactly how it works, but I can say that companies like this are really in the vanguard in the UK of creating capability and ensuring that the UK is going to be in a position to lead in many different commercial areas, from launch to small satellites and a whole variety of additional services. But when we look at what IOSM is, the race for commercial space, what do we mean? Well, the reality is we mean everything from debris removal to transportation to assembly in orbit to human exploration assistance to recycling, or often looking at in-situ resource utilization. How are these things happening? Well, they are happening, and they're happening at a variety of levels. So already we're seeing inspection of spacecraft on orbit, and my earlier reference to the mission extension vehicles, we're seeing refueling. At the same time, we're seeing debris removal by companies like Astroscale. We're seeing transportation of spacecraft moving between orbits from Momentus and D-Orbit and others. We're beginning to see nascent activities like Maiden Space around assembly, and we're beginning to see activities around maintenance as well. And then finally, in the distance, we're beginning to see just the very small vestiges of human exploration assistance and potential in situ resource utilization. Lots of things happening. Based on this, we can see three potential scenarios. Scenario one is basically there is no further development. We stand still as we are, it's business as usual, and logistical support for space is Earth dependent. Scenario two is about limited or partial adoption of in-space manufacturing. We see improved mission autonomy, we see increased safety and mission flexibility, and we see increased capability per kilo of mass to orbit. Finally, in scenario three is a full shift to in-space manufacturing, commercialization, the paradigm shift, new mission capabilities, the abilities to build large parts in space, big structures, spacecraft, etc., and full commercialization of orbit and going beyond. And that's going beyond not just Earth, not just the Moon, not just Mars, but going way, way beyond that. And this allows us to look at new markets, new manufacturing, looking at ultra high quality optics, pharmaceutics, high strength alloys, microencapsulation, and many more. Technologies we can prove on Earth, but we can demonstrate in space, and we can return to Earth for the benefit of society. One example is ZBLAN, a superior optical fiber manufactured in space, currently being made in space, currently being demonstrated as a product which you make in space, you can make to a higher performance than you can make on Earth. It's clearer, it means that you have higher bandwidth, you can transmit more data. And the market sizes you can see on the screen potentially could run to the hundreds of millions. We're also at the same time seeing some of the first potential lunar missions. So lunar by extension of commercialization of space. Why do we go to the moon? Well, the reality is there's not much reason to go to the moon beyond science and preparation for going to the other planets. However, we could go to the moon to look for ice. We could go to the moon to look for materials we can use in local orbit, which we can use for propulsion and for refueling stations. And Spacebit are a UK-held company who are planning to send this very small robot, about the size of 4 hamsters roughly, to the moon this year. I believe they were planning to launch in July this year, but I now think that time scale has probably slipped to November, but an exciting company and one to watch. At the same time, we're also seeing studies into orbital power plants. So for example, where we use effectively the sun to generate energy via photovoltaic cells, converting that into microwaves and beaming those back to Earth. Why do we do this? Well, we fundamentally can reduce our carbon footprint. If we had half a dozen of these stations on orbit, we would be able to supply up to 25% of the UK's energy needs. If we can do that, as opposed to using potentially even wind or solar on Earth, oil, gas, and other dirty carbon-based fuel supplies, or even nuclear, we suddenly can create effectively full sovereign independence for effectively power. And on the Earth, we'd need a microwave receiver of somewhere between 3 and 5 kilometers in diameter. Big, but in reality, a standard airport, international or military, is about that size. And the technology needed to prove these technologies in space are fundamentally not that complicated. In many ways, an orbital solar plant is actually far simpler than having a nuclear fusion power plant. We know the technology needed to go into space, whereas for nuclear fusion, we're still learning how to develop nuclear fusion. Coming right to the end of my slides, I just wanted to flag this out there. At the moment, we have spin turns from the Satellite Applications Catapult out. In my team, which focuses on in-orbit servicing and manufacturing, we have opportunities for spin turns in these areas. An orbital demonstration for industry outposts, so an orbital factually free flying factory, a lunar ice mining and an extraction study, and composite manufacturing in space. And at the same time, we recruit interns throughout the year. If you're interested, please do reach out. Look me up via my contact details on this slide, look me up on LinkedIn, and reach out and say what you're interested in doing. At the end of the day, you're the future who will ensure that we can take the aspirations of what we potentially can do today and convert that into the reality of tomorrow. Thank you very much, and I wish you success and interest for the remainder of the conference.
Amazing. Thank you, Mike, for that fantastic talk. Mike joins me now for a few minutes of live Q&A, which is amazing. And the first question we've had come in is, to what extent does scientific knowledge limit the commercialization of space and what we can achieve in orbit manufacture?
Actually, it doesn't. I mean, realistically, what we've seen is this kind of transition where if we look back to kind of the era of the Apollo, the early days of the International Space Station, etc., it was all about mostly scientific exploration. But that was at the same time really a thinly veiled way of disguising that this was about big space agencies supporting their national defense and aerospace bodies. But it was about science and it was about exploration. Commercialization is just the same. We can take exactly the same lessons from the scientific exploration of space and lever that capability into commercialization. But the great thing now is we've got the ability to say, by commercializing space and doing things, because fundamentally it's about making money at the end of it, the side benefits you get out of that can get kicked back into doing science exploration. So we can build, for example, lower cost Mars rovers. We can build giant telescopes using technologies we might use to build orbital solar, and we can use manufacturing and space techniques for building, a whole variety of deep space probes to go beyond our solar system. So the two are highly aligned and highly advantageous together.
That's really interesting to hear. So are there any missions then that are being prepared with this link in mind? So you're doing something and then saying, "Oh, we could do this actual mission in the future." Is anything else prepared now?
So there's a lot of discussion right now around in-orbit assembly. So in-orbit servicing and manufacturing, IOSM, but a big emphasis on doing that. The early demonstrators about concerning basically building robotic telescopes. And organizations like the University of Lincoln and others have got some really exciting areas around this, as do the Open University, as does Southampton Imperial and Bristol. Ideas about basically how do we build large constructs in orbit using technologies like automated composite manufacture in space, which we want in turn to use to build larger structures, both for manufacturing product in space for use on Earth and in space. But at the same time, there are direct parallels with building, say, a very large aperture space telescope, for example. So yes, you're going to find these projects overlap, because the reality is that academics have as much interest in industrial application as they do in terms of scientific.
Wow. So yeah, lots of opportunities for students in the future as well, by the sounds of it then.
Absolutely. And the diversity of the opportunities are now going beyond just the traditional subjects. So those delegates who are listening, for example, who maybe have non-traditional backgrounds, so maybe are studying subjects like pure, say, chemistry or chemical engineering or construction, quantitative surveying, economics, all of these increasingly have factors. The ecosystem of the commercialization of space isn't just about space agencies and companies like Lockheed and Boeing and Airbus building things. It's about companies who have never done anything in space before, like, for example, John Deere and Caterpillar. The reality is if you want to build lunar habitats on the moon, yes, you could get ESA or the NASA to build you a very expensive habitat, or you could go to someone like Bovis and Caterpillar and say, well, you build complex structures on Earth. Actually, building things on the moon isn't that much more difficult.
Yeah, it's been really interesting to see all these companies that you just wouldn't expect to be working in the space sector then now.
Yeah, I mean, one of the most interesting examples is Rolls-Royce, for example, and their interest in terms of basically now looking at space and seeing deep space propulsion and power for Luna and Mars being on the radar. Hugely conservative company, suddenly wanting to do really exciting things. So, that's exciting. And, I do want to emphasize there are really interesting opportunities out with the spin turns. We as a Catapult are taking on interns, and we're taking more and more. So if you're out there and you're thinking you want to do an internship and you haven't seen it advertised, if you've got an interesting idea about what you want to do to it, do reach out to me and say, this is what I'm interested in, because there's a fair chance that we might well be looking at that in the near future, or we are already looking at it today.
Mm-hmm. Amazing. So what, in your opinion, are the biggest challenges in this for the future?
Probably the biggest challenge is, sadly, it's slightly boring, but it comes down to basically willingness of government to be bold and ambitious. The drive out there is there clearly from an industrial perspective. The drive out there from a commercial perspective is there, but it's convincing effectively both space agencies and government that this is the true vanguard of commercialization of space. The UK has a slightly dubious reputation for space, having in the 60s decided to give up the ability to launch satellites and rockets on the basis that the Americans would do it for us. And the Americans will absolutely do it for us, just at a significant cost, but we lose all the adjacent benefit and innovation at the same time. We're right now on exactly the same precipice. If we don't effectively embrace the commercialization of space, if we're not there with the first companies demonstrating capability, and folks like Josh from Space Forge talking later are prime examples of UK companies who are really embracing this. If government and agency don't directly support these companies, then the risk is that the UK loses the edge. And it's not an edge we can afford to lose, because this is like effectively probably not technically politically correct, but effectively like colonization of North America. So if you don't get in there early, if you don't get in there with your railroads and your shipping and your commercialization, it's very hard to turn up later and go, hey guys, we're going to build a railway. And everyone's there going, well, we've got a railway. We don't need your railway. Well, it's a really nice railway. It comes in blue and yellow. Well, that's great, but we've got a nice railway and we don't need yours. So we have to critically get in there first and demonstrate we have the capability. Part of that is private capital, but part of it, as always, is government incentives, government initiatives, and more critically, and the biggest issue beyond capital is effectively the future workforce. So greater environment to talk to about the future workforce. But unless you're given the right incentives, the right support, and the right opportunities, it's going to be really difficult to ensure that UK citizens, European citizens, that's global citizens fundamentally, can ensure that the UK is a powerhouse for this commercialization. Otherwise, we're going to end up basically being stuck in the 1960s as we were when we abandoned Black Arrow and associate technologies.
Yeah, it sounds like there's definitely a lot that the students can get involved with, and it's such a great opportunity that we have in the UK here. And as the next talks will highlight, I think, the variety of different things going on. That unfortunately, that's all we have time for. Thank you very much, Mike. That was a really interesting discussion after that for me, and I hope the audience as well. So Mike will be on the Discord for more questions. And up next, we have 4 quickfire talks on different areas of manufacturing in space. I hope that you enjoyed those. Thank you again to Mike, and I'll see you soon.
Good afternoon, everyone. My name is Rosa Santomartino, and I'm a postdoctoral research associate in space microbiology at the University of Edinburgh. Today, we are going to talk about space biomining, and particularly what we learned on the topic thanks to the BioRock experiment that we performed on board the International Space Station in 2019. Microorganisms or microbes such as bacteria, yeast, unicellular fungi, and so on perform countless tasks for us on Earth. One of these is indeed biomining. It's basically the use of microbes to extract useful elements from rock ores and mine waste. Because microorganisms are so important for us on Earth, you can imagine how essential they will be beyond Earth. For instance, some of the possible roles that microbes could perform on us on an extraterrestrial settlement include the generation of food and oxygen, the recycling of waste, the production of fertile soil, and also space bioindustries. All these possible roles of microbes beyond Earth have all the final aim to assist life support system by allowing us to use these resources in the place in which we are going to settle, rather than relying on a constant resupply from Earth that, as you can imagine, is not going to be sustainable, especially in a long term. Among these, biomining in space is raising and increasing interest. However, conditions present in space are quite different from those on Earth. For instance, the gravity condition is quite different. Around the space station and in open space, we have a condition called microgravity that is sometimes referred to as weightlessness, while on planetary bodies such as Mars and Moon, we have generally a lower gravity condition in respect to Earth. So before understanding if we can perform biomining in space, we need to understand what is the influence of gravity on these mechanisms. And it is with this question in mind that we performed the first biomining experiment on a space station, the BioRock experiment, that was launched on the International Space Station in 2019. To perform the BioRock experiment, we used 3 different bacterial species that were Syngomyia dissecabilis, Bacillus subtilis, and Cobriavidus metallidurans. And they grew in the presence of a rock substrate. As a rock substrate, we selected basalt. 2 main reasons. The first is that basalt is a generic porous rock material that provided a very good support for the bacterial colonization. The second is that basalt is actually a very good analog for Moon and Martian rocks. So the bacterial culture were grown in the presence of the basalt rock in space in 3 different gravity conditions that were microgravity, simulated Martian gravity, and also simulated terrestrial gravity. But we also had a 4th set of samples that stayed on Earth and represent what we call the ground control. These samples were subjected to real terrestrial gravity. Bacteria grew on both the International Space Station and on Earth for 21 days. So let's get now to the results. What did we discover from the BioRock experiment? The first results that we got was that actually we found no difference in final star concentration between the gravity conditions in space after 21 days of growth. And this is actually a very good result from the point of view of biotechnological application, because it means that they will reach the same final concentration regardless of the gravity conditions. From the point of view of space biomining, we focused on two different type of elements that are the rare earth elements and vanadium. They are all very important and relevant in our everyday life, but also important in industrial applications. We discovered that one of the bacterial species, Sphingomonas dissecabilis, was able to biomine rare earth elements in all the 4 gravity conditions that we tested, and 2 of the bacterial species that are Sphingomonas dissecabilis and Bacillus subtilis were able to biomine vanadium in the space conditions. This means that space biomining is in principle achievable under a range of gravity conditions. And so in conclusion, what did we discover from BioRock? We discovered that first, low gravity is likely not going to be a limit to biotechnological applications in space. And second, we provided the first demonstration of biomining on a space station. Thanks to the success of BioRock, we are now performing a second space experiment, space biomining experiment, that is called BioAsteroid. In this case, we are going to biomine real asteroidal material in microgravity, and we are going to use not only a bacterial species, but also a fungal species, that is Penicillium simplicissumum. So to conclude, what do we expect? What can we expect from the future? Well, there is yet a lot to understand. In fact, we need to learn more about which are the effects of gravity and also other space conditions on microbial processes. We need to select the best microorganism for any given application that we want to perform in space. And we need to understand how to scale up the system to develop space technologies. But last but not least, we also need to understand how to keep the process sustainable. And I want to stress that research is needed, and this isn't going to benefit not only space application, but also terrestrial applications. So in conclusion, I want to thank all the excellent BioRock team, and of course you all, for your kind attention.
Hi everyone, my name is Hannah and I'm a researcher at the Open University, and I'm interested in resources on the moon and how we might use them, and so I'm going to try and give you a crash course in that today. Okay, so first let's take a look back at when we went to the moon around 50 years ago. So the Apollo missions were really short-term missions, just a few days on the lunar surface, able to collect a few samples, run a few experiments, and then return home again. But we are looking forward, and we would like to produce a moon base, somewhere where humans can be present most of the time or all of the time, running experiments, and just kind of that next step for humankind and expanding further into space. And that would require a lot of supplies, a lot of resources. Here's an example moon-based concept here, and it wouldn't necessarily be possible to launch all of those supplies from Earth. And looking even further into the future, let's say a Mars base, this would be an even greater challenge. There's a reason why we haven't sent humans to Mars yet. Mars is, first of all, really far away. It takes around 6 months to get to Mars. So imagine all of the supplies that you need just to get there, and then to live there, and then to return home again. So what if we didn't launch everything that we needed from Earth? What if we were able to produce the resources that we need on the moon? That would mean that we didn't have to launch everything on multiple large rockets from Earth that could be potentially, well, not even possible economically. But let's say we're able to produce those supplies on the moon that could support a moon base, but those supplies could also be used to support missions onwards to Mars. So for example, the crew from Earth, with some of their supplies, could launch into space, and the rest of the supplies, let's say the rocket propellant, because that is one of the largest mass of supplies that we need, they could meet with the crew and launch onwards to Mars, and then once they get to Mars, they could again produce some of the supplies that they need to keep them going on Mars and to help them on their return journey again. So, what resources are there actually on the moon? It might seem like a pretty dull ball of rock, but there's plenty in there. So the regolith is that surface few meters of like crushed up rocks, and this is just a non-exhaustive list of some of the things that we might find in that regolith and some of the applications. So, for example, you might have silicon in the regolith to produce solar cells, or you could use carbon dioxide, nitrogen and water to support lunar agriculture, to grow the plants that you need. You might also find some thorium and uranium to help produce nuclear power on the lunar surface, or even aluminium, hydrogen, oxygen, and then together the oxygen and hydrogen in water to produce rocket propellant. But we can't forget one of the other major resources is just the regolith itself as it is. It can be used as a building resource. So there's the ideas of building roads, launch pads, and bases, and these protective habitats for the crew to live in. And that can be done by melting the regolith and 3D printing with it. So there is many possibilities and many things that we can actually use on the moon, so we don't have to bring everything with us from Earth. But the main priority, or at least one of the main priorities at this point, is oxygen and water, and that's because of the oxygen that can be found in the water, because it's going to be one of the most imminently required resources to keep crews alive and to produce that really that useful rocket propellant that we need so much of. So where is that water? Well, there are two ways that we can find this water and this oxygen. The first is in polar ice. So in the north and south pole of the moon, there are areas, because the sun is so low in the sky, at the bottom of craters, sometimes there are areas that never see sunlight, and so they're extremely cold. And that means that any water that does ever get delivered to the moon, let's say, for example, on a meteorite, okay, most of that water will vaporize, but some of it will, if it strikes one of these cold traps in what we call permanently shadowed regions, it will stick there. And so we think there are quite large deposits found in these cold traps in the north and south areas of the moon. But if we can't go there, there is also the oxygen bound up in the minerals on the moon, in the regolith itself. So here's just an example of some of the minerals that we might find on the moon. And in their mineral structure is oxygen. So you can use some chemical reactions to draw out that oxygen to use to support your crew and produce that rocket propellant. So some pros and cons. Well, polar ice, we think it could be found in large deposits and relatively easy to release from the regolith, just some heat. But they are found in extremely cold regions, and there's no direct solar power. That's the point. They're shadowed, and they're found at really hard to reach places at the bottom of these craters. Now, oxides in the minerals, the benefits is that oxide minerals are found everywhere on the moon. So you could go to areas that are more easy to access, like some nice flat plains, but they require a lot of energy to extract, and they are quite complex reactions, and they do require additional resources that we might need either from Earth or, again, on the moon. Okay, so the next steps. So this is the Global Exploration Roadmap, which outlines kind of the general goal over the next few decades of all the major space agencies. And so, first of all, there's going to be a lot of prospecting missions to identify these resource deposits and where they are, so we can target them. And then we'd look to produce large-scale resource extraction demonstrators to produce the kind of quantities that we really need, and then integrating that into future lunar missions with crews. And then finally, launching those supplies either onwards to support missions to Mars, or perhaps even returning some of those precious supplies to Earth. Okay, thank you very much.
Hi there, my name's Josh and I'm the CEO and co-founder of SpaceForge. Really pleased to be supporting this year's NSSC and delighted to have you join me for this conversation about manufacturing in space and the benefits for our planet Earth. First and foremost, manufacturing in space is incredibly important because it allows us to overcome the barriers we find day to day on Earth. Those barriers are chiefly gravity, atmosphere, and temperature. Now, on Earth, we found ways to overcome all of them in fairly limited fashions. We've developed the vacuum pump, which is now used in everything from the production of electronics to the most efficient way to milk a cow, to centrifuges to be able to overcome the constraints of gravity. And we've been able to invent the oven and the refrigerator to find ways of pushing and pulling temperatures. But by moving production to space, we can overcome all of those barriers at a much higher rate and together. And really, it's almost entirely unique that the space environment is able to provide that. It's almost impossible to recreate the space environment on Earth for a long enough period to be able to produce the things on Earth that are much easier to do in space. So in-space manufacturing is incredibly important for our planet. And that's been able to have been observed really through the past kind of 30 or 40 years of history. Manufacturing in space started on the US Skylab with types of semiconductors. They then took that semiconductor research into the US Space Shuttle using a facility known as the Wake Shield and developed new types of ways to make electronics. And then it moved into the International Space Station. And the International Space Station for the past 20 years has been the most incredible facility for developing new types of in-space production and research. We've seen everything made from new composites and alloys all the way through to pharmaceuticals, including drugs and vaccines. Probably the most notable of these is made in space's fiber optic cable, ZBLAN. ZBLAN is a glass composite. When you try to produce it on Earth, it's incredibly cloudy, and to be honest, it doesn't look very good. But if you make it in space, you get a glass composite which offers you a fiber optic cable tens of times more efficient than the fiber optic cable you can produce on Earth. And we're able to translate that research across some of those fields I've mentioned, like semiconductors, composites, and alloys. So by moving production to space, we're able to overcome the barriers really in the state-of-the-art technology that's found on Earth. That means that in space we can produce composites that can be used in things like wind turbines to help us generate more electricity. We are able to use materials like semiconductors, for example, to be produced in space, which back on Earth can translate into power reduction of about 60%. And that power reduction translates into preventing about 75% of CO2 from ever being generated. And that can only be achieved by manufacturing in space. So for the past 20 years, the ISS has been the most incredible research platform for leveraging microgravity and the rest of the space environment. That's allowed us to do things like unlock new materials, alloys, and pharmaceuticals. But quite simply, it's not the factory. And in order to really scale in-space manufacturing, we kind of need to look beyond the space station. And that's for three reasons. The space station is getting old, and its age is contributing to contamination. That contamination essentially comes from the fact that it sits in its own orbit, which has been expelling oxygen, air conditioning, coolant, and various other things for the past 20 years. So if you're trying to do something that requires incredible levels of purity or cleanliness, it's actually quite difficult to achieve that with the ISS. Secondly, are the astronauts on board. So the astronauts on board and the station keeping that the station regularly goes through basically means that the microgravity environment is continually being disrupted. And that disruption translates into grain defects when you're trying to produce protein crystals or electronics. And lastly, after you've gone through the pains and the tribulations of trying to make something on the ISS, you're then incredibly limited by the next time you can come back. So returning from the space station is a real issue. Of course, we've seen the advantages emerge like SpaceX's Dragon, and it's no longer it being the Russian Soyuz. But both approaches are very similar in the way that they come back. They rely on technology which is known as ablation. So they melt away some of the elements of the capsule on their descent. And when they come back with a pretty hard bump. And that bump and the shock impact that's felt there can also essentially ruin some of the experiments and lead to the loss of some of those manufactured products. So what we need to do is we need to find a new way of leveraging the space environment in a way that's sustainable and allows you to come back from space much more gently so that you can really unlock the benefits. If coming back from the ISS is difficult. We need to find ways of creating new return solutions so that we can really maximize the space environment to produce products there that can't be created on Earth for the benefit of humanity back on our planet. At SpaceForge, we've been looking into creating return solutions from space, which are much more gentle than the current available infrastructure, and most importantly, are flexible. Flexibility is really important because once you've made the product, you don't want to be hanging around for the next few months waiting for the next return mission from the ISS. You need to get your product back so you can integrate it as quickly as possible into the industries that will benefit back on Earth, like renewable energy, electric vehicles, quantum computing, and telecommunications. So what we've been doing at SpaceForge is we've been developing the Forge Star. The Forge Star is an independent platform capable of manufacturing new products and materials in space that can return independently. Now, most importantly, by independently, what I mean is that we go away from the space station. In fact, we go higher than the space station to at least 500 kilometers altitude. That allows us to access a better quality of vacuum and much longer durations of microgravity because we don't have to worry about station keeping. So at SpaceForge, we're developing a full suite of technologies to help us develop the Forge Star platform and really scale in-space manufacturing to new levels. In doing that, we're able to create a positive impact back on our planet. And that's really what we're all about. At SpaceForge, we have a full suite, a full team of engineers across mechanics, robotics, electronics, systems, software development, and operations. And this year, we'll be looking to recruit at least 3 new early careers across those engineering functions, and we'll be looking to bring on 2 fully paid internships as well, at least for the summer, but to be possibly extended for a year. So please do come and speak with us, and I look forward to having a conversation with you. Thank you very much for your time.
Hi everyone, I'm JJ. I'm General Manager of Made in Space Europe, a Redwire company here in Luxembourg, and I'm excited to talk a little bit with you today about in-orbit manufacturing, a new frontier in the space sector. So we are Made in Space company, recently acquired by Redwire. Probably you might know us from putting first 3D printer in space on International Space Station. We did it several years ago, and since then we are adding more and more equipment and more technologies that are working around in-orbit manufacturing. Our first, we have several payloads on International Space Station, several generations on the of the 3D printers that are helping astronauts to perform their daily activities. We started from there by developing a 3D printer that will be able to 3D print the different items. First in microgravity, it was pretty tricky to help astronauts. We printed already, I think, more than 150 different objects on board ISS. It helps astronauts really perform their daily activities, since typically when you are operating on ISS, you need to plan everything in advance. So if you forgot something, that you forgot certain parts, probably you need to wait a few months to get it. Thanks for 3D printing, we're helping to support astronauts and simply email this thing to ISS when by CAD file to be 3D printed. However, our goal was not only limit ourselves to print things, manufacturing things only on ISS. It was always building large structures in space, outside, in thermal vacuum environment. Therefore, after conducting several generations of 3D printers on board of ISS, we qualified them to also work in thermal vacuum condition. So we could build actually a spacecraft that is able to manufacturing and assembly large structures in space as a free flyer. And several years ago, we were granted by NASA by a contract called Archinaut 1. It's a first spacecraft that will be able to manufacture and assembly a large structure in space as a free flyer. To demonstrate benefits for 3D printing in space. I think it's a very exciting mission, so I recommend you to follow it. What we are demonstrating by Archinaut, it's 3D printing very large boom, very large beam that will help to roll out solar panels. So the satellite that typically has a limit on how much power it has, that is driven mostly by the size of deployable solar panels, could actually have much longer solar panels than it's allowed by the current technology of the deployable solar panels. And thanks for this solution, the very small satellite can have 10 times higher power budget than the same satellite with standard deployable solar panels that is available today. So imagine where you could use payloads, you could use onboard processors that are consuming 10 more powers, 10 times more power. What capabilities it's opening for your satellite, and it's one of the first demonstration of how industry actually could benefit from 3D printing. There are certain things you always would like to have in your satellite. It's of course smaller mass, higher power budget, smaller volume. And thanks for this technology, we are sort of breaking the paradigm that is in space industry on how satellites are built and what they are capable for. So we are using 3D printer. We are building in-house, and also we'll be using robotic arms to not only print things, to not only manufacturing things, but actually to assembly bigger structures. And I wanted to share with you that Made in Space was set up in US, first in California, then our office in Jacksonville. However, a few years ago, we set up also our office in Luxembourg to build here and produce robotic arm that will enable us to increase capabilities of assembly, since since in-orbit manufacturing, it's not only about manufacturing, it's also about assembly, manipulating things to build complex structure in space. So Archinaut 1 is about printing a boom that will build future solar panels. However, by adding robotics there, we could accomplish much more in near future. I'm emphasizing this because probably a lot of you might be interested in pursuing your career in this direction, and this is available to be done in Europe. We are talking about here about future. And there's plenty of application of in-orbit manufacturing, and right now with Archinaut 1 demonstration mission, it's just the beginning of technology demonstration. It's interesting contradictory requirements we have, since space is expensive, mostly because the launch is expensive. And we could develop very innovative launchers. However, there will be always certain price to launch your payloads, your spacecrafts, and there is plenty of harsh conditions for this launch, mostly rated for shock and vibration, where you need to modify your design mostly by adding mass to actually survive launch conditions. And in the same time, when you are launching very stiff, mass optimized elements with additional mass to actually survive launch, from the other point, from economical point of view, you want to reduce your mass to minimum, because this is driving a cost of launching your element to space. Therefore, one of the solutions is actually in-orbit manufacturing, when you could simply launch your 3D printer with a robotic subsystem that will be designed to survive this launch. But despite of launching your structure, you could just launch feedstock that will be used by 3D printer to build what you are looking for and assembly what you're looking for in orbit. That might be much lighter and much cheaper than something that you would need to design on the ground and later launch. In the same time, you can't and you will never be able, despite of what big launchers we will have of launching certain big elements because of the limit of launcher fairings. Therefore, 3D printing is actually allowing you to print these objects in space, such as solar farms or solar panels. And we reach certain limit of the technology. For example, for telescopes, for James Webb Telescope is showing that we can have bigger telescopes with traditional technology, with deployable technology. So we need to find out different solutions, and 3D printing is an answer for that. I will finish with that. I'm happy to answer on your questions later. We are encouraging you to start your career in space manufacturing robotics, since this is a new frontier and a lot of exciting things will be happening here. Thanks a lot and have a good conference.
Thank you to all those speakers. I hope that's given you an amazing insight into the variety of opportunities available in orbit manufacturing and all sorts of in-space manufacturing, and hope it inspired you to get involved if you're interested in it. So yeah, big thank you to all of those. Those speakers will now be on Discord if you have any questions for them. And Josh from Space Forge will also be at the Careers Fair. Just to mention that the Careers Fair is a great time now to go. Hope that you can make the most of that over lunchtime. There's lots of companies still there who are really eager to talk to you about opportunities for them for you to join them, if there's any potential job opportunities. And also, if you just want to go and find out a bit more about what they do, then there's a huge variety of organizations there, and it'd be great if you could go and meet them. So we are going to lunch now. We'll be back at 1:20 for 2 talks on this stream. We'll be hearing about how to become an astronaut and all sorts of other opportunities from Zaria Serfontein, and also about, after that, hypersonic flights from Clément Civrais. On stream 2, we will have a whole stream of talks on quantum technologies for space. So I hope you're looking forward to those, and I will see you soon. Have a good lunch.
Hello, everyone, and welcome back from your lunch break. We're now going to hear a talk from CGI before we hear from Zaria Serfontein on trying to become an astronaut while doing a PhD, and then Clément Civrais on hypersonic flight.
Hi everyone, thank you so much for coming today to the National Student Space Conference. My name is Dr. Chandra Tapasya Fisher, and today I'm going to tell you a little bit more about CGI. Founded in 1976, CGI is among the largest IT and business consulting services firms in the world. We are insights-driven and outcomes-based to help accelerate returns on your investments. Across 21 industry sectors and 400 locations worldwide, our 76,000 professionals provide comprehensive, scalable, and sustainable IT and business consulting services that are informed globally and delivered locally. Our first space project was actually in 1974, and from then we've continued to have great presence in the space sector. We've worked to increase the value of client space investments whilst combating ever-growing security threats to space assets and information. We deliver complex mission-critical space software systems for clients across Europe, Australia, Asia, and North America, supporting satellite navigation, communications, and operations, space science to space-enabled applications. I first wanted to tell you a little bit more about myself. I'm an Earth observation business development consultant with coming up to 5 years in the Earth observation world. I've worked at another Earth observation-based research and services provider. I've worked in the Earth observation department of the European Space Agency as a young graduate trainee. I have a PhD in marine and numerical geophysics, as well as an MSci in geophysics, both from Imperial College London. Some of the projects that I work on that I'll talk a little bit about more in detail later include ESA's Digital Twin Earth Precursor for Food Systems and Truth's Phase AB1 PDGS. I also often work with the European Space Agency and UK Space Agency to understand upcoming bids, find partners for the best consortium team, and lead bids from conception through to negotiation. Some additional responsibilities that I hold include being Vice Chair of UK Space Earth Observation Committee. I'm also an Executive Committee member of BARSC, or British Association of Remote Sensing Companies, and I do a lot of advocacy for STEM outreach, hence why I'm here talking to you today. So for our technical graduates, I just wanted to give you a little briefing on what you'll be doing and the skills that are needed for this. CGI can provide IT career opportunities that open up lots of possibilities and give you the chance to make a real impact on the world. We are here for the future, with our transformative projects creating lasting legacies across some of the world's most vital and exciting sectors. You'll get to work on high-profile public and commercial clients, stretching your talents to deliver improvements to complex systems that make the everyday simpler. You'll make a real difference in people's lives. The types of graduates that we are looking for at CGI demonstrate a genuine interest and an absolute passion for technology. Our technical graduates will be working or studying towards any degree discipline. If you come from a computer science or STEM background, this would be an advantage. Depending on which business unit you would like to join, we will consider graduate applications from those who have achieved or are working towards a minimum of a 2-2. If you're not on track for this, but have extenuating circumstances, then your application will also be considered. For the summer of 2021, we aim for our technical graduates to play a big part in the solutions that we deliver to our clients and they have worked on some of the biggest project roles, such as programming, testing, or developing. We typically have graduate vacancies across our various industries, which include central government, defense and intelligence, energy and utilities, financial services, and space. And we also occasionally take graduates into corporate functions. However, whilst you might start in one area of the business, the opportunity to move internally is huge, offering you the opportunity to grow your career in the direction that you want under permanent contract. We'll have a link on the page where you can find out more details and where to apply. Now for a topic closer to my heart, which is CGI in space. I'll be taking you through some of the projects that we've been working on. The first one is the Digital Twin Earth Precursor project I mentioned earlier, for which I am the project manager. A digital twin is a replication of a physical system digitally, providing real-time insights and visualizations to help decision makers. There is a range of different data sources, such as computer-aided design, building information models, Internet of Things, etc. They incorporate multidisciplinary, multi-scale models, allowing interaction of data and creation of new scenarios. Digital twins are normally built for a specific purpose and to enable data sharing in a community. Examples include aircraft engines, digital cities, the models of buildings, wind turbines. Hi everyone, thank you so much for coming today to the National Geometry Underpinning Terrestrial and Helios Studies. You'll soon find that the space industry loves an acronym. It's a satellite mission whose sole aim is to reduce our measure of uncertainty from other satellites by a magnitude or more, specifically to help with climate change measurements. CGI are in charge of PDGS, or Payload Data Ground Segment, and this involves how do we receive the data from the satellite to the ground and how we process it and distribute it to relevant parties and stakeholders. That brings a close to this presentation. I hope you found it insightful and that you've learned a little bit more about CGI and what it does. Please don't hesitate to reach out if you have any further questions, and thank you so much for listening. Have a great day.
Thank you very much to CGI for that wonderful talk, and apologies for that little technical mishap on our end there. If you have any further questions for CGI or would like to talk to them informally, you can visit them at our careers fair right now. Now we're going to be hearing a talk from Zaria Serfontein. Zaria is the team lead for the Low Earth Orbit Negligible Impact Drag Augmentation Systems project at Cranfield University. The team will be taking part in parabolic flights with ESA's Fly Your Thesis program to qualify the design for microgravity. Zaria's talk will cover a number of topics: space debris and how her PhD is trying to address it, what it's like to be part of the Fly Your Thesis program, and how to hone your astronaut skills while doing a PhD.
Hi everyone, I hope you're having a great time at this year's National Student Space Conference, even if it's looking a little bit different this year. Thank you for tuning in to listen to me, and thank you to UK SEDS for giving me the opportunity to talk about my PhD. Today, I'll be taking you through how to do a PhD while secretly trying to become an astronaut. I actually submitted the proposal for this talk before ESA announced that they were going to be looking for astronauts, so that's just a happy coincidence. My talk today is going to cover 4 main topics. Firstly, I'll be going into astronaut skills. What are the transferable skills between doing a PhD and trying to become an astronaut? Next, I'll be going into one of the primary challenges that my PhD is trying to address, which is space debris and the ever-looming threat of the Kessler syndrome. After that, I'll be talking to you about taking part in this year's Fly Your Thesis campaign, which is the next big chapter in my research. And then finally, I'll finish by giving you some insight into doctoral research in general, the good, the tiring, and the exhausting. So let's get started. With the last call for astronauts approximately 11 years ago, up until recently, we only really had a vague idea of what the European Space Agency would be looking for if they're selecting astronauts. Now that the call is finally reopened, they've released a very handy checklist of physical, technical, and personal attributes, which they believe make a great astronaut. I wanted to set the scene by sharing a quote from Canadian astronaut Chris Hadfield's book, An Astronaut's Guide to Life on Earth. In this quote, he talks about always being prepared and credits his conscious, methodical approach to preparation as the main reason of why he got to Houston. I never stopped getting ready, just in case. However, I never thought, if I don't make it as an astronaut, I'm a failure. This really resonated with me. Aspiring to be an astronaut can sometimes sound like an unrealistic or almost childish goal. And at the moment, there aren't that many opportunities in this line of work. You have to accept the fact that it's not only going to be possible that you'll never achieve this goal, it's actually quite likely. That's why I get involved with projects that I'm genuinely interested in and passionate about. But in the back of my head, I always have a checklist of things that I know will improve my chances of becoming an astronaut. And I make sure to keep my checklist up to date, always getting ready just in case. On their application form, ESA lists a PhD or equivalent degree as an asset to the application. That's already a great reason why doing a PhD will get you one step closer to becoming an astronaut. But why is it seen as an asset? And how can you use your time as a doctoral student to improve your chances of getting chosen to go to space? These are my theories. Compared to other STEM fields, it can be difficult to get started in the space sector. Undertaking a PhD is a great way to gain experience in the space industry. Although the pay doesn't really stack up to doing a full-time job, the exposure that you get to the industry is really valuable, and you can shape your research in such a way that it sets you up for a career in the space sector. Next is management. As a PhD student, you are in charge of your own studies. It's up to you to set realistic goals to make sure you have the resources to achieve them, efficiently manage your time, and constantly update what the impact of your research is going to be, making sure that you stay relevant. You'll have countless examples that highlight your decision-making capabilities, your flexibility, and hopefully that shows that you're able to remain calm in difficult situations. The ability to rapidly assimilate and synthesize complex information was taken directly from ESA's website. As a PhD student, a large portion of your time is taken up by absorbing a lot of complex information and then applying that information to your own research. Although it may not seem like a skill, being able to read quickly through papers, understand the main concepts, and pick out the main points is something that does get easier the more you practice. I'm paraphrasing here, but the only difference between messing around and science is writing it down. ESA wants to be ensured that you are passionate about sharing your work. As an engineer, writing papers and giving presentations didn't really come naturally to me, but it's so important to make sure that something good comes from your work and that you're able to help others with your research. I've had lots of opportunity to share my knowledge, as I'm doing today, and I've had lots of practice tailoring information to present my findings to different audiences, a really valuable skill to have. Teamwork is not something that's often associated with PhDs, but in my own experience, the space industry is highly collaborative. There are so many opportunities to work with other students, other departments, other universities, even industry. You just have to be able to identify them and be ready for rejection. I've had a lot more applications rejected than accepted. And then finally, we have external opportunities. As a PhD student, you're in a unique position of still being a student, able to apply for student competitions and student funding, but your previous experience gives you more weight in these applications. Since you're managing your own time, I've also found that it's much easier to volunteer with societies outside of my studies, which will help you improve the technical and soft skills that you're not able to improve through your studies alone. Two major themes for the space sector in recent years has been the growing number of objects that we're actually sending to space and the recognition of space debris as a critical threat to future and ongoing missions. Last year, almost 80% of the satellites that we launched were small satellites. In the graph, you can see that we've gone from launching tens of satellites in 2010 to launching more than 1,000 satellites last year. Due to these amazing advancements in satellite technologies, space is now more accessible than ever. Unfortunately, the increase in launches has also added to the already high number of objects that are hurtling around the planet. The simulation on the right gives us a visual representation of this challenge, showing that the density of objects in low Earth orbit is much higher than anywhere else. This video was created in 2019 and it's already out of date. We now have 34,000 objects larger than 10 centimeters in diameter orbiting the Earth, of which 2,700 are active satellites, showing how rapidly this situation worsens. The number of objects are particularly concerning given the speed that they're traveling at. Objects that are orbiting the Earth are orbiting at almost 8 kilometers a second. With that much energy, even small pieces of debris can have massive consequences. Also, debris from satellite collisions don't just fall back to Earth and burn up in the Earth's atmosphere. They continue orbiting the Earth, posing a serious threat to operational satellites. We seem to be getting closer and closer to the feared Kessler syndrome, which is where a big collision happens. The debris from that collision goes on to impact other satellites, causing a massive ripple effect, which goes on until pretty much nothing in orbit is left unscathed. Objects in low Earth orbit will eventually deorbit themselves, but this can take tens, hundreds, or even thousands of years. A lot of research is now going into looking at ways to actively remove debris by sending up spacecraft to remove it from low Earth orbit. Others are also working on recycling centers and creating a more sustainable space environment. But this on its own is not enough. Since we're planning to launch so many more satellites in the next few years, we need to make sure that the future satellites are equipped with the tools to remove themselves from orbit at the end of their mission. One way to achieve this is through drag sails. In the video, you can see the deployment of one of our drag sails, first in real time and then at a quarter speed. Drag sails are deployed at the end of a satellite's mission. They increase the effective area of the satellite, increasing its drag and its rate of orbital decay, allowing it to re-enter and burn up in the Earth's atmosphere. At Cranfield University, we've developed and qualified two drag augmentation systems, the Icarus and the deorbit mechanism. 3 of these sails are now in orbit, and 2 of the devices have actually successfully deployed their sails. They are low-mass, simple designs intended to have a minimal impact on the host satellite, allowing them to be fitted in a very late stage of the design. Since there are currently not sufficient economic or financial incentives to include a deorbit system in your design, we want to make sure that they are as easy to implement as possible. As part of my PhD, I am now involved in further developing a more scalable and adaptable hybrid design, which we'll be testing as part of ESA's Flyer Thesis campaign. Just before Christmas last year, we received the amazing news that we were one of the teams selected for this year's European Space Agency's Flyer Thesis campaign. This program, run by ESA and Novaspace, gives students the opportunity to test and experiment on board a series of parabolic flights simulating microgravity. At the end of October this year, we'll be taking part in 3 flights, each giving us 30 parabolas, with each parabola giving us approximately 20 seconds of microgravity. In total, this is a full 30 minutes of microgravity for our experiment. We were one of 3 teams selected to take part this year. Team DZH Dynamics and Team Zeus will also be on board with us testing their own experiments. ESA also have 2 other altered gravity programs. Spin Your Thesis simulates hypergravity conditions ranging from 1G to 20G using a large diameter centrifuge. Drop Your Thesis is another program which simulates microgravity by using a drop tower. We'd originally considered other platforms, but the parabolic flight allows us to have multiple deployment opportunities, allowing us to qualify our sails, and the available space in the aircraft far exceeds that of the other platforms, which means that we can qualify larger, more scalable designs and start to test the limits of our design. We'll be testing our experiments on board the Novaspace's Air Zero G platform, which is an Airbus A310 aircraft. When Novaspace isn't training astronauts or helping students and industry test their experiments in microgravity, they're hosting some really interesting events. Back in 2018, they hosted a race between Usain Bolt, French astronaut Jean-François Clairvoy, who's also the CEO of Novaspace, and French interior designer Octave de Gaulle. Some of the stunts in the Tom Cruise reboot of The Mummy were also filmed on board the aircraft. They've even hosted a club event in Zero G, inviting Big City Beats, World Club Dome, and a host of celebrities and VIPs. And now we're going to be using that same platform to test our drag sails. I'm the team lead for the Leonidas team, which stands for Low Earth Orbit Negligible Impact Drag Augmentation Systems team. You can see the rest of the team in the image on the right, hanging out with Paxi. As well as trying to get some practice in Zero G to help with my astronaut application, the main purpose of the experiment is to study the deployment dynamics of our sails in Zero G. We've reached the limits of what we're able to test in 1G conditions. So by testing our sails in microgravity, we'll be able to make more scalable, adaptable, unobtrusive, and robust sails. You can follow our journey on Instagram, Facebook, LinkedIn, and Twitter. We'll be keeping you up to date, telling you a lot more about our experiment, telling you about testing in microgravity in general, and uploading a lot of videos of us in Zero G. We might even be hosting a competition or 2, so do keep an eye out. And finally, I'd like to briefly make a few comments about my PhD experience, the good, the tiring, and the exhausting. It doesn't take a genius, it takes determination. You don't have to have a certain IQ to take on doctoral studies, you just have to be willing to put in the work. It can sometimes be very difficult to keep yourself motivated, especially if you're the one setting the deadlines and the goals. So more than anything, you just need determination to get yourself across that finish line. There's a lot of opportunities once you actually start your PhD. I've already talked about all the ESA altered gravity programs, and UKSETS hosts a number of competitions and events throughout the years that students can take part in. Generally, you're encouraged to attend events and conferences, and organizations such as the Royal Aeronautical Society will help you out with funding. As an example, last year I applied for a project with the UK Space Agency and a more ambitious project to send samples to the International Space Station. Even though these weren't successful, at least it just shows that there are plenty of opportunities in the space sector. Use your time to boost your CV with relevant skills. I've always wanted to do more software engineering, and even though it's not currently directly related to my course, I'll be attending a beginner's Python course at Cranfield soon. It's a great way to boost up your skills for your CV. A great way to find the skills that you actually want to add to your checklist is by looking up job adverts in areas that you want to work in after your studies, and then looking at their desired and required skills. Finally, and this is a big one, pick something that you are passionate about. 3 years is a long time to be spending on something that you don't enjoy, and it would be easier to convince other people to care about your topic if you're enthusiastic about it too. And that's it from me. Thank you so much for listening today. I'm happy to take any questions now, and feel free to contact me after the conference as well. These days, it's probably easier to contact me through the Leonidas platforms or to find me on LinkedIn. Hope you enjoy the rest of the conference.
Well, thank you very much for that absolutely fantastic talk, Zaria. For all our attendees, we're now going to go to a live Q&A session with Zaria. So please, if you have any questions about her talk or her work on Leonidas, make sure to submit it via our Q&A function. So Zaria, our first question is, what type of external opportunities would you recommend taking part in? And what if these are not accessible to you?
Brilliant question. So I think I'm going to focus mostly just on the UK, because that's kind of the side that I know most about. I think first up is definitely if you have a UKSETS branch anywhere in your area, try and join that. Usually universities have them, or if you don't have one, we can help you set one up. If you can't get into touch with them directly, just become a UKSETS member. So already by becoming a UKSETS member, you have a membership email that goes out every month, and that alerts you to opportunities that you can take part in. There's also other external ones that you can join, like there's an ESA forum that you can join where when you're on their list, they send you updates on their activities. But I think it's nicely encapsulated by UKSETS. So their email usually has kind of all the opportunities that are available to university students.
I think that's fantastic advice, and I'd like to echo that to anyone watching. Definitely try and get involved with UKSETS and as many opportunities as you can across the country. Now I've got one more related to your work on space debris, and that is there any prediction of how likely it is that the Kessler syndrome occurs in the near future?
Really good question. Yeah. So I think it gets updated so often that this answer changes so often. At the moment, it's not a huge concern. So there's a lot of space in space. So at the moment, the likelihood of collisions happening are quite low. And because we have situational tracking, we're able to keep track of satellites and we're able to move them out of the way before a collision occurs. But with the rate that we're increasing satellites in low Earth orbit, like increasing them tenfold in the next 10 years, that's no longer going to be the case. Especially since we're sending up a lot of smaller satellites that don't have their own propulsion capabilities. So basically, once you've sent them up, they're up there. If they're on a collision course with another satellite, you can't move them, you can't get them out of the way. So it's something that very near term is not super likely, but considering the amount of objects we're sending to space, it's going to become very likely very soon.
Wonderful. We've got a question more related to your work on Leonidas here, which is, How will the drag sails be made adaptable for a variety of spacecraft, and can they be used on larger satellites?
Yeah, that's also a brilliant question. So at the moment, we have ones that are kind of different shapes and different sizes, but they've always been limited by the size of the satellite because they're either attached to one side of the satellite or they're kind of covering one panel of the satellite. But what we're trying to do with the new design is we're trying to break it down into different modules so that we have one module for the boom, one module for the sail itself. And if we do it in a modular approach like that, you can kind of scale it to whatever size satellite you have, whatever shape satellite you have, and you can make sure that it's free of any obstructions.
Thank you very much. That's another fantastic answer. I'm afraid that's all we have time for on the Q&A front. But to everyone listening, Zaria is now going to be available on our UK Centre Community Discord server for some further Q&A and informal discussion. So thank you again, Zaria, for a fantastic talk and a wonderful Q&A session. It was an absolute pleasure having you.
Brilliant. Thanks for having me.
Now we're going to be hearing from Clément Civrais. Clément is a PhD student at the University of Glasgow, working on the development of novel chemical reaction models for hypersonic flows. He holds 2 master's degrees in aerodynamics and aeronautics, and Clément will be discussing hypersonic flows, the study of which is integral to understanding the physical phenomena surrounding a spacecraft when entering a planetary atmosphere.
To this Tsuda contest about aerospace. Here in this light talk presentation, I'll try to introduce you to hypersonic flight, hypersonic vehicles, hypersonic aerodynamics, and what's so special about that. Obviously, I will not be able to cover everything about hypersonics. So I really advise you to give it a try to the recommendation books I'll give you at the end of this discussion. So let's start right now with these supersonic aircrafts. So on the left, you have the Bell X-1, which is the first aircraft that breaks the speed of sound in 46. So look at the design of this aircraft. So slender body, thin wings, about 9% thick, sharp leading edge, sharp nose. Now move on to the F-104, which was designed for a maximum Mach number around 2. Slender body, thin wings, sharp leading edge, sharp nose. Now move on to the Concorde, which is also an aircraft designed for a maximum Mach number of 2-ish. Slender body, thin wings, sharp nose, sharp leading edge. Excellent design for supersonic aircraft. So now if I ask you to design an hypersonic aircraft, what would be a starting point? Would it be the extrapolation of this slender body concept until the ultimate design of a needles, basically? Would it be flying needles? Here are hypersonic vehicles. So on the top right, you have the X-15, designed for maximum Mach number of 7. So look at the wings of this X-15. They aren't so thin anymore. And look at this nose, mostly this nose, which isn't sharp. It's blunt actually. And now look at the X-20 dinosaur, which has also a blunt nose. Now look at the ultimate space shuttle. It was designed for maximum Mach number of 25. The slender body assumption is 3, not the case in this particular design. So by that, you see that hypersonic and supersonic are widely different, and supersonic design is not usable for hypersonic flights, right? So now if I ask you to define for me what is hypersonic, and I'll ask you the maximum Mach number above which the flow regime is qualified as hypersonic. In most of your textbooks, you'll see that the maximum Mach number is around 5-ish. And this is a rule of thumb definition, because there is plenty of things to think about when you're dealing with hypersonic flight and hypersonic vehicles. So just to clarify all that, I'll quote P.L. Roy from the Von Karman Institute, who said that almost everyone has their own definition of the term hypersonic. If we were to ask everyone to name a Mach number above which the flow of a gas should properly be described as hypersonic, there would be a majority of answers, round about 5 or 6. But it would be also possible for someone to advocate and defend number as small as 3 or as high as 12. So clearly there are a lot of features that characterize hypersonic. So I'll try to briefly explain you what is hypersonic. So there are 4 major characteristic phenomena. So thin shock layers, entropy layers, viscous interaction, high temperature effects. Because of this kind of short amount of time, I'll only focus on the last item, so high temperature effects. So look at on the right, the Apollo reentry scheme. So this is capsules flying at Mach 36. So you see this characteristic bow shock, which is detached from the surface of the capsule, right? And precisely, you also see temperature behind the shock wave, which is around 11,000 degree Kelvin, right? Now, just to give you a quick comparison about this temperature, the surface temperature of the sun is around 6,000 degree Kelvin. So namely, the temperature related to this capsule reentry case is about almost twice as the surface temperature of the sun. So there's a lot of energy produced in this specific case, and a lot of chemical reaction happens. So basically, you have the internal degree of freedom of the molecules, which are excited, so namely the vibrational, translational, and rotational, that allow dissociation, recombination reactions to also produce radical species, and can also produce ions elements. So you in an environment that is composed with a lot of specific chemical species, which is not the case for supersonic flights, and even more for subsonic flights. So just with that, hypersonic is really interesting and totally different from supersonic because of the chemistry that is involved. So I'll quote John Anderson from the University of Maryland to give you an insight of what is hypersonic. So hypersonic flow is that portion of the more or less extreme height Mach number spectrum where certain physical phenomena becomes important that were not so important that lower supersonic speed, so namely the chemical effects. What phenomena? Thin shock layers, entropy layers, viscous interaction, and high temperature effects. These are the physical phenomena that distinguish hypersonic flow from supersonic flow, and that is the definition of hypersonic flow. So if I wrapped up all these elements in a 3 bullet points conclusion, so clearly the design of an hypersonic aircraft is totally different from supersonic aircraft because cannot be extrapolated due to the severe high condition that hypersonic vehicles facing, namely a temperature around 10,000 degree Kelvins. And this high temperature produce a lot of physical chemistry effects. So all these chemistry are involved and play a key role, which is not the case in supersonic cases, supersonic flights. So in terms of recommendation readings, I really encourage you to read the Anderson Hypersonic and High Temperature Gas Dynamics, which is really nicely written. Anderson is well known for its writing style, and trust me, it is a smooth journey through hypersonic reading this book. So I hope you guys you enjoy this kind of small discussion about hypersonic, and thank you for attending. If you have any question, please drop a message.
Thank you very much for that wonderful talk, Clément. That was a brilliantly put concise summary of hypersonic flight and why it's important to consider in the space industry. Now we're going to go to a live Q&A session with Clément. So if you have any questions for him, please make sure to submit them via our Q&A function. So again, thank you very much for speaking. We do have a few questions here already. And the first one is, why is the boundary between supersonic and hypersonic flight so blurred?
That's really a complex question to kind of answer, because the physics between supersonic and hypersonic do not change from green to red, if you wish. And there is a lot of element to consider in this kind of transition from supersonic and hypersonic. And the reason for that is clearly the energy involved in such flights. And well, defining hypersonic as a Mach number around 5 or 6, it's really a sum definition for me, as a lot of things had to be included with this definition, namely chemistry behind that and all the transport properties that are really complex to define.
Thank you. No, that's a brilliant answer. The second question here is, why can't hypersonic design, unlike supersonic design, be extrapolated?
Well, it's simply a matter of the energy involved again. Just to recall, the surface temperature of the sun is around 6,000 degree Kelvin-ish. And if we think about the Apollo reentry capsule, which was facing a surface temperature around 11,000 degree Kelvin, obviously you have a lot of chemistry reactions that now can happen, which is not the case in supersonic. Usually, the design of a supersonic aircraft is built around the idea of limiting the strength of the shock waves, basically. And in hypersonic flight, you cannot just do that, because the temperature is way too extreme and the surrounding conditions are way too extreme. So the idea is just to design a shield that could just help you to reach the ground or the earth in a safe condition.
Thank you. That was another brilliant answer. And another question here is, why was the Concorde stopped?
Well, that's a complex question to answer, to be honest, because I do feel that there is some politics incomes behind that we do not have at the moment. And well, in terms of safety, I feel that the design wasn't kind of polished enough, and that's the reason why at the moment we do not see supersonic flight to transport a random person from a city to another. Actually, on that, the Europe kind of already signed a contract to develop a new version of the Concorde that follows the new restriction in terms of acoustic and all the aerodynamics properties for safety.
Thank you. And we have one last question.
Yeah.
And that is there anything beyond hypersonic, or do the effects of hypersonic flow just become more severe?
Well, on the far extreme hand of the Mach spectrum, there is the hypervelocity, but well, there is not fixed boundary, to be honest. And after hypersonic, I would say there is only extreme condition, even more extreme than hypersonic flights are. So I do not see any new domain of aerodynamics after hypersonic.
That's wonderful. Thank you very much. Well, yeah, I'm afraid that's all the questions that we have. But thank you so much for a fantastic talk and an amazing Q&A session. We really appreciate it and loved having you here at the conference. So if anyone has any further questions for Clément, or you'd like to talk about the topic with him further, you can go to our community Discord server for more discussion with him. We'll now be going to a short break, but afterwards we will be back for talks on climate science and space medicine on this stream, and a panel on space debris on stream 2.
Welcome back. Up next, we've got a talk from the Institute of Physics, which is going to be followed by a talk from Dr. Ranjini Swaminathan about an overview of the UK Earth system modelling. That will be followed by Lauren Church discussing space medicine. But first up, we'll give you the IOP.
I've really benefited a lot from being a member of the IOP. It gives me the opportunity to
get insights, network with fellow physicists.
It's added variety to my life.
It's allowed me to get to know physics students in completely different fields.
Share ideas and thoughts.
Lots of events.
Physics world magically arriving at my doorstep every month.
I felt like I had a support network.
I'm really looking forward to meeting employers from different industries, helping me make a more informed decision about what I want to do in the future.
Hello everyone, my name is Julian Guasada. I'm the Student Engagement Officer at the Institute of Physics, and I'm joined today by members of our student community, Charlotte, Sarah and Mark. Hello all out there. We'd like to introduce you to the IOP and invite you to join our community. The purpose of this video being to shed a bit more light on the Institute of Physics and how we can help you broaden your knowledge of physics as a discipline and as a sector. How our resources can help you develop your career and employability, and how our community of physicists can help you broaden your network. So we'll all be pitching in as we go through the slides. Feel free to check out the website and look up what we're talking about as we go.
So, who we are. The Institute of Physics, the IOP, is the professional body and learned society for physics in the UK and Ireland. We seek to raise public awareness and understanding of physics and support the development of a diverse and inclusive physics community. As a charity, we're here to ensure that physics delivers on its exceptional potential to benefit society.
And then just a bit about what we do. Our members are active in education, academia, business and the public sector, using physics and its applications to transform our lives and society. So we support our members' career aspirations and professional development, and we also provide a platform for networking and collaborating, which enables our members to help us shape the future of physics.
Thanks, Mark. So IOP membership provides tailored support and opportunities throughout your career as an undergraduate. You would join as an associate member, progressing to member upon once you leave university. And it's our aim, our job really as a society, to support you through every stage of your career, through to a fellow, hopefully, where you're making a distinguished contribution to the field. And we do that by providing an access to a wealth of resources, activities and events to support your career development and enhance your experience wherever you are, whatever you are doing. And in students' case, obviously that means enhancing the experience of university itself to build skills, employability and discover the wider sector, preparing you for the end of university and beyond. So becoming a member means part of joining something a bit bigger than you and making a difference to society. I encourage you all whilst at university to try to share your passion for physics as much as you can and be an advocate for physics. Really, the three pillars of the organisation, what we seek to give to members is community, knowledge and career development. And on screen, some of the ways we enable you to do that. There's tons of developmental and social opportunities, networking, resources, over 50 special interest groups in every area of physics and 150 conferences plus a year. Associate membership costs just £15, and we've developed really a sustainable ecosystem of different activities and groups of students and members, all organising fun physics stuff to create a multitude of opportunities for you to get involved. And we're able to do that really because we have such an active student membership and community, the wonderful people who are co-presenting today. We collaborate with our members wherever we can. Students lead on so much of what we do because that means hopefully what we do is relevant and useful to you.
Yes, I'll talk a bit about the affiliate societies. So the IOP affiliate with physics and related societies every year to give them support, funding, and connect them with a huge community of students across the UK and Ireland. And last year, we affiliated with over 45 societies and supported events such as forums, conferences, society fairs, quizzes, trips, you name it, the IOP was there to help fund and support. For example, my society, Queen's University of Belfast, we affiliated back in 2016 for the first time. And we got lots of funding and support from the IOP. They even were able to sponsor our physics football team, which we went on to win the league. And that was purely down to the IOP sponsorship, I'm sure.
So Campus Ambassadors organise fun physics activities at universities around the UK and Ireland, encouraging conversations around physics and providing a space for the students to have those conversations, whether that's a physical social setting or an online social setting. I've been a campus ambassador for a few years. This year, campus ambassadors are at over 30 universities. If you're interested in the scheme or you want to meet your ambassador, then write to us. We'll be doing lots of fun stuff this year, especially online. So on behalf of the other campus ambassadors, we hope to see you there.
The Student Community Panel is a group of volunteers from each region in the UK and Ireland. I represent the West Midlands, and we work with the IOP and other student groups as the International Association of Physics Students, where we host and organize national annual activities like CAPS, the Conference of Astronomy and Physics, and Planks, which are held at different universities each year. We also share insights into our student experience to the IOP so that they create opportunities for our members. This year, this group worked on a lot of activities over the summer. So they worked on employability workshops, webinars, and coding workshops on Python and LaTeX. Also, they ran online quizzes with prizes, and they are currently working on a podcast that will feature conversation with different physicists across the UK from different backgrounds.
Thanks, everyone. So some events that are coming up. If you have a campus ambassador at your university, they'll be putting together fun, informal welcome events to introduce you to the other physicists. Oops. And we have online workshops and webinars roughly every 6 weeks, like the free coding workshops that Sarah mentioned. If you're a female physicist, please do come along to our Employability Half-Day Conference, taking control of your career as a female physicist on 9th December 2020. And our student panel will be working on a sort of equivalent online skills event. The dates will be forthcoming for that. Typically, social restrictions permitting, we run a range of fun events throughout the year, like Planks this year at Kent in February. Really popular student physics, written physics competition across a weekend, or our CAPS conference, Physics and Astronomy conference, or our trips to science facilities, giving you new skills and a greater understanding of the field in a fun, welcoming environment.
Yeah, so developing your knowledge is really important as an undergraduate. Becoming a member of the IOP enables you to further that development and to further develop your knowledge of physics through the IOP. So lets you do that through a number of different platforms, such as the Physics World magazine, which is a fantastic physics magazine delivered to your door every month, or else on the app. And I was actually able to use the Physics World magazine, an article from that in my master's project. So it is a really useful tool that you can use. They also send out lots of monthly info in the newsletters, so you can hear about what the community is up to. There's also the IOP journals, and I think there's over 70 of them, and they cover every area of research within physics that you can imagine. They've also got a bunch of special interest groups to connect with scientists in your area of interest. And there's also lots of different events and conferences throughout the year with discounts for members. And I think Julian said there's over 150 of them throughout the year.
So your future. The IOP are really good at supporting your future. You can volunteer at events, festivals, or in schools. They also organise lots of talks and events for you to attend. Physics World, like Mark was saying, has really helped me understand the field better, and it's also helped me support my studies and shape them to support my future career. Physics World Jobs is also a really helpful website to look at for your future career prospects.
Yep, and on that note, we have an online career development hub for our members, brilliant resource full of guides and tools, simulators, application builders, videos from experts across the spectrum, everything really careersy that you would ever need, but for a scientist kind of profile. So please do check it out. If you are to join, really the main message we have for students is community, knowledge and career development. Make the most of your time at university and to get involved in physics outside the lab as well as inside. Meet different people, challenge yourself, volunteer and share your passion for physics. Employers love it and it will support you to become a better scientist, a more rounded individual who can communicate their passion and hopefully inspire others to do it too. I think this year more than ever, it's worth thinking about connecting to a community that really supports its members to be connected and informed, so that we can use this time to develop ourselves as scientists and as we seek to address the challenges we all face as a society. So we do hope you'll join us, and I hope to see you at some of our events in the future. Thank you so much for listening, and best of luck this year.
To the Institute of Physics. They are at the Careers Fair at the moment, so if you're interested, head on over and chat to them. Next up, we have Dr. Ranjini Swaminathan talking about an overview of the UK Earth System Modelling project. Over to you, Ranjini.
Hello, my name is Dr. Ranjini Swaminathan, and I'm going to talk a little bit about the UK Earth System Model project. I'm going to give you an overview of the project. As you can see from all the logos on this title slide here, the UK ESM project is an ongoing collaboration between several research institutes in the UK, and we have some international partners as well. And I will talk a little bit more about what, who those partners are in a bit. But I'm based at the University of Reading, and I'm part of the National Center for Earth Observation. So my talk outline is like this. I'm going to introduce and motivate the use of Earth systems or Earth system models by talking a little bit about climate change and the Earth system. Then I'll introduce Earth system models, specifically talk about the UK ESM project, and then talk about possible opportunities for research within that project. To give credit where it's due, some of the slides from here and some images have been contributed by others in the UK ESM core development team, which I'm a part of as well. Climate change in the UK. So this slide kind of illustrates a very simple fact about how the temperature has been changing, how climate has been changing in the past few years. So if you notice here, this bar-coded plot here, darker reds means hotter and darker blues are colder. You'll see that the 5 coolest years are kind of early on in the century, and 5 warmest years in the UK have all occurred within the last 17 years. So clearly this is a signal that we can't miss. The planet is warming. This global warming or the increase in temperature, as the slide tells you, the average temperature has risen by about 1 degree Celsius since 1850. 1850 is considered when the Industrial Revolution took place and a lot of heavy industrialization started. Before then, it hadn't varied by more than 1 degree Celsius over all human civilization. So that's like 12,000 years. Greenhouse gases, as you might all be familiar with, like carbon dioxide, trap heat in the atmosphere and then warm the earth. And humans definitely contribute to this increase. This plot on the right-hand side shows you how the temperature is actually changing or increasing. You can see there are ups and downs in consecutive years. One year might be warmer, the next year might be cooler, and so on. But there's a clear trend that is increasing, showing an increase in temperature. So what are Earth systems? So given that we have the climate is changing, we want to be able to better study what the Earth is like, the climate of the Earth is like, and so we want to model different physical, chemical, and biological components of the Earth system. Not only that, we also want to see how they couple or interact with each other, like how ocean contributes, processes in the ocean contribute to warming on land or vice versa, and how these processes affect each other, and the movement of things like greenhouse gases and nitrogen and oxygen and stuff through all of these systems. And also we want to be able to look at what happens when humans enter the picture, like things like land use changes and agricultural use, deforestation, and things like that. So we want Earth system models to study the past and the present climate. And how do we study if these Earth system models are doing well in terms of simulating our past and present climate? We use observational records for validations. So we look at observed records of temperature, precipitation, precipitation as rainfall, and other such things. And we see if our Earth system modeling capabilities are good, where we're lacking, and what we need to do to improve. And then we're going to use all this knowledge to look at how the Earth system will change in the future under different possible scenarios, not just with physical climate changing, like temperature increasing and more greenhouse gases coming and so on, but also socioeconomic pathways, such as what if we go hopefully bent on industrialization? What would happen then? What if we take a far more sustainable path? Then can we keep emissions down? Can we reduce warming? We will also be able to investigate tipping points. Like, is there a point of no return? Like, what if the temperature goes beyond a certain point? Would things cascade from there on, and would we never be able to come back? The impact. So are we going to see more drought? What does that mean for farmers in the UK? Are we going to see more tropical storms? Are we going to see more cold weather patterns like we've seen recently in the UK and in North America this year? Mitigation and policy. So you might have heard of the Paris Climate Agreement. So this is basically a whole host of countries coming together, international collaboration to see how we can build policy to prevent the Earth from warming and basically saving our planet for future generations. How do we go about it? Here's a very simple illustration of a climate model. So as you can see, the simplest of models is quite complex. So there's a whole lot of processes here, interactions between the atmosphere, biosphere, lithosphere, and the gas exchanges and so on. And all of this is actually modeled in an Earth system model. How do we do that? We take the Earth, as it were, and we look at this in terms of like gridded cubes. So there's a horizontal and a vertical component. So the horizontal is defined by the latitude and longitude, and the vertical grid is the height or pressure in the atmosphere. In the oceans, the vertical component would be the ocean depth. And for each of these grid cells, we model all the processes you saw in the previous slide, and that's kind of encapsulated by this picture here. So you can see a lot of complex representations over here. So how are these processes represented? In the form of physics equations and chemical reactions, as you might have all have studied recently, in a high school or in the first or second year of your university education. So, so these would be things like the ideal gas law, the Navier-Stokes equation, and also key processes for biogeochemical variables like carbon, oxygen, and stuff. So how is ozone formed? Like how do oxygen molecules react to form ozone and things like that? So all of this. So these equations basically represent those processes. And then these equations in turn are written as computer code for huge machines to crunch. So as you can see, this was not, you can imagine that this was not developed overnight. So since the mid-70s, development has been very consistent, and huge progress has been made in recent times. So in the mid-70s, we had the atmosphere, and then in the mid-80s, land surface models were added to the atmosphere models. And we come all the way here to the early 2000s, where you have like ocean and sea ice, aerosols, carbon cycle, dynamic vegetation. And finally, we also have continental ice sheets, and the UK's Earth system model, the first version, so UK ESM 1, is basically right here, as advanced as any Earth system model can be, because we have dynamic ice sheets as well in the model. So you can imagine, if you were, all kinds of complex processes going in to build this model. So what does the UK ESM itself look like? These are the basic components. So you have what is called the unified model, which represents the atmosphere. And then you have JULES, which is the terrestrial biogeochemistry model. Then you have UKCA for the atmospheric chemistry, MEDUSA for ocean biogeochemistry, SICE and NEMO are the sea, ice, and ocean physical models. And then there's bicycles, which is the ice sheets model. And that pink block here in the middle is the OSS coupler, because you can't have these models just doing things on their own. You need them to interact and feed in information. Like every 3 hours or every 30 minutes or 40 minutes, some input would come from the ocean model into the atmosphere and into the land, and so on. So the coupling is done by this a component called OSS. So I mentioned a little bit about what we use these models for and stuff. So I'm just going to have show you a very brief illustration of one of the things we can use it for. So this is basically surface temperature. And I also mentioned to you scenarios like, what if we took a sustainable pathway versus intensive fossil fuel development? So if you look at this video, it starts from in the beginning of the century, all the way going up to, you can see the years at the bottom right corner. So it goes all the way up to like 2100. And you can see what our view is of the Arctic here, really. So you can kind of see the UK somewhere down here. But primarily the focus is on the Arctic. The top left is a sustainable pathway. Is what would happen to the Earth if we took a sustainable pathway, which is basically green energy and so on. The bottom right is where we focus on the intensive fossil fuel based development. The other two are somewhere in between. And you can right off see as we go to the end of the century that this dark blob, right? It gets darker and bigger in the bottom right, which shows that warming is quite high. Compared to pre-industrial times, if we take up a fossil fuel intensive development pathway. So I also mentioned that how we evaluate these models, you have to trust these models. So one way of doing that is by using observations, and the range of observational data sets, right? They can span, so these observations can be collected from a whole variety of sources. You could have weather stations that actually record temperature and measure rainfall, or you could have satellite data like this. So I'm from the National Center for Earth Observation, and we provide a lot of data sets like this, gridded data sets. This example you're looking at here is solar-induced fluorescence, which is considered a proxy for vegetation. So you can see the Amazon forest being highlighted over here, and the equatorial forests here, like near Indonesia and so on. So this can be used to see if our models represent vegetation properly. So we have this for seasonal and annual variables. So this is all gridded, and basically you can compare grid cell by grid cell, how well the model is doing. And as you might have already realized, we need huge machines to crunch through these, those equations that I showed you. So at the Met Office, we have very large machines, and we also need efficient and computationally efficient code to actually run these models effectively. So UKASM is not just the machines and the science. There's also people who actually do the science. So it consists of the core development team, which has experts in atmospheric chemistry, aerosols, clouds, oceans, land and vegetation, model evaluation, Earth observations, as well as project management. It is a multi-center collaboration, as I said. So the two primary partners are the UK Met Office and NERC, which is the National Environmental Research Council. Other organizations such as the National Oceanographic Center, the British Antarctic Survey are also part of this. Academic partnerships, several scientists and researchers and universities that are part of these organizations participate in developing the UK Earth System model, and they use the model as well, providing very valuable feedback. International collaborations, there are a couple of big overarching projects that UKASM is a part of across Europe, and different modeling groups in different countries in Europe come together to share ideas and to partner with on these science projects like UKASM. And UKASM itself contributes to the Intergovernmental Panel on Climate Change, or IPCC, which you might have heard of again. It's the United Nations international collaboration to study climate change. We also contribute data to the UK government and climate data services, from where users can basically access data. Model development. So I'm going to talk a little bit about opportunities within the UKASM. So these are opportunities for model development, building computational efficiency of the model, and doing better model evaluation. So these are the three broad topics that I could think of where new scientists can basically participate in. So if you were to go on to gain expertise in any topics, you could potentially be a contributing member to the UK Earth System model. Outside of the core UK ESM itself, you could still work with Earth System model data and actually use that data to do impact assessments, to look at things like floods, drought forecasts for the future, and see how this might affect your community, the world in general, as well. You could also be part of the mitigation and policy. So you could take up climate justice activities. You could be part of the government trying to help with mitigation, to help cut down emissions and to make the future safe for everyone living here, not just in the UK, but the world over. So these are some of the opportunities that I thought I could highlight for budding careers and for young people who might want to take up a career in sciences and to do with Earth system modeling. That's it from me. So if you have any questions, please let me know. I will be around.
Thank you. Thank you so much for the talk, Ranjini. So I'd like to kick off the Q&A with a question about your modelling. So obviously they're very complicated things. Has the COVID crisis affected the way that we consider climate change? And do you expect our reaction post-COVID to make it to be different?
Hello, I'm sorry. Could you repeat the question, Alex?
Yes, of course. So given the recent...
I seem... Hello? Sorry.
Sorry, if you don't mind bearing with us while we sort out this technical issue.
This had happened, right?
Ranjini, can you hear me? Yes, please. I believe Ranjini is struggling with...
Apologies, I don't know what happened. Everything was going fine.
Sorry, we'll just wait for verification that we're all good on the platform, and then we will go ahead with your question.
Yeah, I'm really sorry. I haven't had any problems at all recently, so I'm not sure. Sorry.
No worries. So I'm going to kick off with a question. Due to the COVID crisis, has it affected the way that you model, with the large models that you kind of described in your presentation? And do you expect our reaction, has it changed the way we're going to behave for the good in terms of climate change?
Right. So we actually, so I mentioned in my talk, so there's the UK Earth System model is part of a group of models called coupled models. So coupling there is basically the different components getting together. And the whole project is called the Coupled Model Intercomparison Project, or CMIP. Mm-hmm. One of the MIPs that they very quickly put together when the COVID crisis started was called COVID MIP, to quickly see if reducing emissions, based on what we saw actually happening with, air traffic shutdown and things like that, if that, how much of an effect it had, how many years it would have to run. So those experiments, some of them are still running, but we're starting to see some initial results now for what if we ran, if all of us behaved the way we did last year for 5 years, what an impact that would have on the planet and so on. Yes, those experiments, and they're showing some, quite nice results. So one thing that they do show is that just a year or two may not make a difference, but in the long term, you could possibly, be on a more sustainable pathway, so towards keeping global warming to under 2 degrees.
No, that's really interesting. And we've got a question in from Isla. What is the estimated year when we will not be able to stop climate change?
That's a personally say that we're probably past that point. We really hard. The aim on act is instructive work. More. We have a problem. So.
Unfortunately, we are really struggling with Ranjini's Wi-Fi, so we apologise for this, but I think that's going to have to end our Q&A as we are running out of time. So up next, thank you Ranjini for joining us and really enjoyed that talk. We think that climate change is a huge area and UK SEDS are actually due to be announcing something quite exciting soon. So keep an eye out on that. Next up, we've got Lauren Church, who is a fourth year student at King's College London as a medic, and she is going to be talking to us about space medicine. So without further ado, I'm going to hand over to Lauren.
Hi everyone, I'm Lauren and I'm going to be talking to you about space medicine and how it can relate to other jobs in the space sector. So I thought I'd tell you a little bit about myself before I start. I'm currently a fourth year medical student at King's College London, and last year I completed my Masters in Space Physiology and Health, also at King's. I'm a member of the Parabolades, and we're a 4-person postgraduate research group looking at the pre-flight medical checks that are required for commercial suborbital spaceflight. I was part of the group that founded the next generation of aerospace medicine at the Royal Aeronautical Society, and I'm currently the deputy chair of that group. Last month I had a paper on space nutrition, more specifically the nutritional adaptations required to optimize performance during spacewalks, accepted to the Journal of the British Interplanetary Society. And last year in March, I was fortunate enough to have the opportunity to go and work at Kennedy Space Center and develop 2 experiments which were investigated on the ISS. So it's pretty clear that space is pervasive throughout my life, including in my hobbies. I thought I would brighten up the slide with the little picture in the bottom corner, which is a model of BB-8 that I crocheted during lockdown last year. So how this talk is going to work is I'm going to give you a very brief overview of what happens to the body in spaceflight, and I'm going to talk about some of the operational space medicine aspects as well. And then talking about how space medicine can relate to you if you are outside of the medical field. So let's start off with that kind of broad view of the body in space. The first thing I'm going to talk about going top to toe is the psychological aspect. So space is an austere, remote, isolated environment, and this can cause a great deal of psychological stress for astronauts. They're away from their friends and family, they are in a confined space with 5-6 other people, and they are living and working in that confined space as well. So this causes a great deal of psychological stress, the isolation involved, the removal from the ground crew as well. And then there's the so-called overview effect, where astronauts look down at the kind of curve of the Earth, they look down and see no borders between countries, and they start to feel small or insignificant in comparison to the enormity of the Earth below them. And a lot of astronauts have talked about this kind of mentality shift after they come back from space, having seen that. Next is the neuroocular changes involved with spaceflight. So when you go into microgravity, there's no longer the action of gravity holding fluids down inside the body. So you get this headward fluid shift, and this can increase intracranial pressure. The skull is a fixed volume, and therefore if you have an increase of volume within it, you get increased pressure. This pressure then relays onto the back of the eye, and you get changes including globe flattening. So the eye becomes flatter in shape rather than round like it is normally. And this can change astronauts' vision. They have a shift towards long-sightedness. And many astronauts resort to using reading glasses when they're in space to try and counteract this. This is something that we only really discovered when humans started staying in space for longer. So the onset of these symptoms is generally between 3 to 6 months for men and 6 to 8 months for women. It's not known yet how longer duration missions will affect this condition, but it's certainly something that needs to be looked into once we look at permanent habitations in space. So going from a long-term condition to a short-term condition, next I'm going to talk to you about vestibular adaptations. So there's a phenomenon known as space adaptation syndrome, where astronauts feel almost motion sick for their first between 24 and 72 hours in space. And this is due to the kind of mismatch of signals between what their eyes are perceiving and what their vestibular or balance system is perceiving in terms of movement. So if you've ever felt motion sick, it's very similar to that. Then the cardiovascular system. So that fluid shift that I talked about earlier has an effect on the heart as well. The receptors in your body that regulate your blood pressure are at heart level and head level. And so if you get that fluid shift upwards, like I talked about before, you're going to get an increased pressure on those receptors. Therefore, your whole body blood pressure drops while you're in space. Because of this, when astronauts come back to Earth, they often find it difficult to stand for long periods of time without fainting, just because you get suddenly blood pooling in your legs again, and you don't have the blood pressure to be able to maintain blood flow to the brain. In terms of respiratory changes, the lung tissue is not very dense. There's a lot of space for air to enter. And you get what's called the slinky effect on Earth. So if you were to hold up a slinky, the density of the coils increases as you go further down. This is similar to the lungs. The tissue is more dense at the bases than it is at the top. Then when you go into microgravity, the tissue becomes uniformly distributed. And so this affects the structure of the lung in microgravity, but it changes when you return to Earth. It's one of the few systems that doesn't have long-lasting changes. In terms of gut, digestive and endocrine changes, it's been shown that astronauts have a preference towards carbohydrate-rich food while they're in space. And this indicates a state of physiological stress. Humans are known to crave carbohydrate-rich food when they're stressed. There's also a change in your sense of taste when you go into space. So due to that kind of congestion and fluid shift that I talked about earlier, it's a bit like having a head cold when you feel like you can't taste anything. Astronauts experience the same thing, and a lot of them report wanting kind of Tabasco sauce and spicy food, just because the feeling of heat in the mouth replaces what they've lost in taste. And in terms of endocrine changes, so your endocrine system is responsible for your hormones. There are changes in your sleep cycle, so your hormones that regulate your sleep cycle, because you have day and night cycles lasting about 90 minutes on the space station. And there's also high levels of cortisol, which is secreted by your adrenal glands, which sit on top of your kidneys. And your systemic level of cortisol is generally indicative of the amount of stress that your body is under. So it's clear that spaceflight is a very stressful environment for the body. And then finally is your bone and muscle changes. So your bone breaks down over time in space. Your bone is consistently being broken down and built back up to maintain its strength. But in space, it's broken down more quickly than it's built back up. And this is because you get this gravitational unloading. So in microgravity, you don't have the weight of your body impacting on your bones. And this means that over time you lose bone mass. And this means that astronauts are more susceptible to fractures when they come back to Earth. And a similar thing happens with muscle. Muscle, as I'm sure you all know, is a use it or lose it. If you don't work certain muscles, they become atrophied or small, and they shrink over time. And this happens in spaceflight as well, particularly with muscles that are referred to as postural muscles, so muscles which hold you up when you're sitting or standing on Earth. And these are muscles that act over long periods of time without getting tired. But if they're suddenly unloaded and unloaded for a period of time, they shrink and become less strong. and this can be a real issue when astronauts come back to Earth. Now I'm going to talk to you about the operational aspects of space medicine. So if you think about it, if there's a medical problem on Earth, doctors will prescribe drugs or a surgical intervention to kind of manage it, or you'll have routine checkups. Now, the way that drugs act is different in space. There's a whole field devoted to space pharmacology, and this includes both how the drugs act in and of themselves and how they interact with the body. Many drugs, including kind of key drugs like antibiotics, are less stable in space due to microgravity and radiation, and this means that they're not as effective after a duration of time in space. Also, the way that your body absorbs and excretes drugs is different, meaning that our entire medical practice may well change as we look to live permanently in space. Space surgery is another thing that hasn't yet been perfected. If you think about it, during an operation, as soon as you cut into the skin, there's blood. And in microgravity, this will form like a bubble around the operation site. So different ways will have to be developed in order for space surgery to be carried out safely and effectively. There are also logistical issues. So I talked about those regular checkups before. If your doctor is on the ground and you're in space and you only have contact through a video conferencing system, you know, there's logistical issues involved with that in terms of examination and being able to even just see the patient or the astronaut. And this greatly changes the way that you practice medicine. And if you look at the image on the slide, this is an ultrasound scan, and that's one of the only imaging modalities that they have in space to look at the human body. And this shows the internal jugular vein of an astronaut. Now I've traced out the external boundaries of the vein with red lines, and if you look at that X in the center, that's a blood clot that's completely occluding the internal jugular vein. Now, this was found in an astronaut completely incidentally during a research study. But then suddenly, when faced with this incidental finding of a blood clot, doctors on the ground had to work out how to treat it so that the astronaut wasn't in danger. And this brings me on to my next point, which is resources. There is a very, very limited medical supply on board the International Space Station. And this is mainly due to launch costs. You know, it costs several $1,000s to launch even a single kilogram of mass from Earth. And so you can't take a whole broad range of medical equipment that you might never use. And this means that, you know, if you have a limited range of drugs aren't as effective over time, and you have limited access to the astronauts, suddenly the way that you practice medicine is completely different. And then finally, there's ethics, which the medical ethics of spaceflight would be a whole talk in and of itself. But a common example that I like to kind of pose to people to make them think about the ethics of space medicine is CPR in space. The way that you do CPR in space is completely different to on Earth. You know, I think everyone's seen kind of basic life support videos where you do chest compressions on someone. But if you don't have a ceiling or a floor, how are you supposed to do chest compressions when you're floating and the patient's floating? So not only is the way that you do CPR different in space, but if your CPR is successful, that person is going to need very intensive medical care. And that's something that's not possible in spaceflight, given all of the things that I've talked about before. And therefore, can you call it ethical to start CPR on someone if you know that you don't have the ability to care for them properly, should that CPR be successful? Now, the answer is, of course, yes, but you know, you need to think about these things, to think about the ethics of your medical practice as we look to journey further and further from Earth. So the next question is, why is space medicine important? You know, a lot of the people watching this conference are engineers and physicists, and you might be thinking, well, why does this matter to me? Well, anywhere that you have humans, you need medicine, you need doctors. And if you look at statistics from spaceflight, from other extreme environments such as polar expeditions or submariners, humans are the most likely component of a system to fail. There's a statistic that says that there is more likely to be a catastrophic failure resulting in the evacuation of one of these colonies because of the human body 10 times more frequently than any piece of equipment that they will come into contact with. And that means that, you need a medical team to support the human part of your system in order to keep everything running smoothly. But if humans are so likely to fail, why do we take part in human spaceflight at all? Well, humans provide an insight that you can't get from robotic exploration. I mean, I like many other people, watched the landing of Perseverance a few weeks ago, but if they talk about the Apollo missions, the astronauts saw a funny looking rock, so they picked it up and brought it back with them. A rover would never be able to identify that and have that intuition and that curiosity to do that themselves. And therefore, human spaceflight teaches us a huge amount about the universe and that we exist in. Also, to consider in space medicine is crew system integration, so the interface between the human and the equipment that they interact with. So if you take a look in the bottom corner of this slide, this is the ARED, the Advanced Resistive Exercise Device, and there's one present on the space station. There's also a treadmill and a bike. Now, if you look at the way that this person is using this device, the interface that they have between themselves and the device isn't fixed. But on the space station, they have shoulder harnesses that hold them down to the device so that they don't, when they apply pressure, they don't separate from the device. And the way that they interface with the device that they're using is also included in space medicine. And that has knock-on effects on the kind of engineers who design these products. And therefore, you need to include medics in your discussions. You need to have the human at the center of the design that you are carrying out. And with that, I'm going to say thank you very much. I'm happy to answer any questions that anyone might have.
Thank you so much, Lauren, for that talk. So now we're joined by Lauren and we're going to ask a few questions. So to start with, Lauren, what do you think about kind of the big projects such as Artemis and how it has an effect on our understanding of medicine?
I mean, I find the kind of looking at long-term missions and permanent habitations in space is a really exciting opportunity in terms of human spaceflight generally and our kind of exploration of the solar system that we're in. But also, you think about space medicine and you think about kind of taking care of astronauts' health, but there's actually a lot of other applications and implications of the study of space medicine. So, I refer to them as up and downstream applications. So things that are developed on Earth that can then be used in space medicine. So a lot of the kind of advancements in medical imaging technology, there's now remote guided ultrasound and things like that can be used on the space station or when we look at having a kind of lunar or Martian habitat. But there's also techniques that we will develop for space medicine as we kind of live in space for longer that can then be applied back down to Earth as well. So I think, not only will we learn a lot about the way that partial gravity environments affect the human body, there will also be operational aspects that we develop in order to deal with the kind of issues that we face and the tenets of the spaceflight environment that we can then apply back down to healthcare on Earth as well.
No, nice. So kind of building on the big the big mission concepts as well then, how big a challenge do you think it is for any talk of humans going to Mars? And from a medical perspective, how close are we, do you think, to being able to achieve this?
I've had discussions about this before with various people in the space industry. And, we talk about the advancements that we're making in terms of kind of propulsion technologies and the fact that we can now kind of get there and in theory land and whatever. But the one thing that will not change is the human body. There's that statistic that I mentioned in my talk with the human body is more likely to fail than any other kind of piece of equipment that humans come into contact with. And so we can't make advancements on the human body, and that is where kind of space medicine comes into play, because you have to be able to deal with those issues as they arise. I think it's important for us to consider that space is an incredibly hostile environment for the human body. You know, the kind of radiation and everything else, it will end up affecting humans quite vastly. A 6-month mission to get to the surface of Mars, it has as much of an effect as 6 months on the ISS, and you know, the average mission to the ISS is 6 to 12 months. So beyond that time, we don't really know how space will affect the human body, whether those detrimental effects will continue to worsen, whether they'll plateau. There's so much more that we have to learn before we're properly ready to get there. And things that they use on the ISS at the moment, so for example, the exercise machines that I talked about, if you are on a 6-month journey to Mars, you might not have space in the capsule to have those exercise devices, or you know, you might not have the resources that you need to be able to have all the countermeasures that we currently do. So we're going to have to take everything that we've learned already and make it more compact as well.
No, thank you for that. So kind of sticking on the ISS theme, I've got a question from Isla. Do you think there should be more medical supplies on the International Space Station?
This is a really interesting question, and there's a whole branch in the NASA Space Medicine Office purely devoted to medical planning and medical mission kind of operations, and looking at, you know, the cost benefit analysis of whether you take, I don't know, certain antibiotics as opposed to painkillers or anti-nausea medication or whatever. And it is a very, very fine balance, because if you think about in a hospital, you'd put up a bag of fluids, and you might give a litre of fluids, and that weighs 1 kilo. So, and you then have to factor in the launch cost of that kilo of 1 litre of fluid that you might give over 20-25 minutes. So everything is vastly more expensive when you think about launching it, and therefore they kind of have a bare minimum in terms of medical supplies on the ISS at the moment. And that's fine for the ISS, because if there is a medical emergency, which, you know, touch wood, there hasn't been, but you can evacuate using the Soyuz and bring these people back down to Earth. Albeit that's not what you want to do, but there is that possibility that you can have them back down on the ground within a few hours. But as we look to, you know, kind of habitats on the moon or on the surface of Mars, you're going to need to have more specialist care capabilities, because you're not going to be able to evacuate them back down to Earth. So I think as we journey further, self-sufficiency is going to be more important. And therefore, things like looking at kind of 3D printing and in situ resource utilization will be paramount in terms of what we're capable of.
No, thank you for that. So interesting. And kind of building on this with the kind of medicines in space, a question from Alex Wood: how can we deal with the deterioration of medicines themselves in space? Is that an issue that we currently face?
That is, again, a really, really interesting question. And I wish that I had kind of hours and hours to talk about everything. There's so much research going into space pharmacology at the moment. And I think the University of Nottingham has some really interesting research that's going on at the moment. A friend of mine did his master's thesis on the use of antibiotics in spaceflight. And, you know, it's a huge topic in and of itself, but the environment causes the medications to become more unstable over time, and that means that their kind of shelf life is shorter, which means that if you don't use them after a certain period of time, they will no longer be effective. And so that's what I mean when I talk about kind of, we're going to have to be self-sufficient. We're going to have to find a way to manufacture these in space, because you can't be launching, you know, kilos and kilos of extra medication every few months just because the ones that you have will expire. And there are certain, you know, if there's a medication that you don't use very often, but you might need an emergency scenario, you can't keep that resupply going just to kind of have it there just in case. So there's a whole kind of operational planning aspect to consider with that.
That's such an interesting point about kind of planning in advance and the self-sufficiency that is required for us on these long-term missions. Just kind of slightly taking it away from this. So a question from Annie. Last year, you were selected to send worms to space from the Kennedy Center, and I remember this because you were due to speak at the previous NSSC, but unfortunately, you had this incredible opportunity. Could you kind of elaborate on this a bit more? Like, what did you hope to learn from it, and how does it contribute to space medicine?
Yeah, so like you say, I was actually supposed to speak last year at NSSC, and a colleague of mine, Dr. Nina Purvis, took over my speaker slot, and she did an incredible job. But I was out working at Kennedy Space Center. I developed 2 experiments which were launched to the ISS and investigated. And firstly, it was an incredible opportunity. You know, I think everyone who loves space has like a kind of bucket list item that they want to work at NASA or, you know, launch experiments to space or whatever. So yeah, it was a great opportunity. And I had 2 experiments. One of them was looking at plastic degradation by a particular type of worm in microgravity, but the other was looking at the regeneration of a type of flatworm called planaria. And so generally, if you take a planaria and cut the head and tail off, it will grow another head and another tail. But they were previously investigated on the ISS, and I think 1 in 15 grew a head on each end, so it had 2 heads. And this is a mutation that's kind of like 1 in a billion on Earth. You know, it's really, really rare, but they found it more frequently on the ISS. So we were looking at like why this happens, and looking at looking at certain medications which would up and down regulate certain stages of this regeneration pathway, and the potential implications for that on Earth are to do with kind of stem cell regeneration and looking at stem cell therapies as well. So that's it. There are potential applications for investigations of that nature in space. So,
and I think we probably have time for maybe one final question, and this is probably quite a big one, and a lot of people will be wondering. So, recently, ESA have just made their call for astronauts, and I don't know if you've seen a bit of a UK SEDS plug here. We've got we're supporting people getting their healthcare certificates. Would you be able to kind of elaborate on why everyone needs to get a healthcare certificate before going into space? And secondly, kind of maybe talk a bit about the para astronaut role this year and why that's possible, and kind of just a bit more detail on that, basically.
Absolutely. So the kind of call for astronauts has been put out, and they require a certain level of medical certification, and it's the same kind of certification that you'd have for professional pilots as well, and that's because there are certain aspects that you need to test to make sure that you're kind of healthy before you go into space. So they require a certain level of vision, of hearing, and things like that. They require a certain capacity for you to be able to act as a professional astronaut. And this is because astronauts have a safety critical role. If there's ever an emergency evacuation or anything like that, those things are safety critical, both for yourself and for the other members of the crew. The idea with the para astronaut kind of call is that, you know, we're starting to open up spaceflight to more and more people. The specifications for professional astronauts have been so narrow for so long that actually, you know, the effect of spaceflight we only have been able to study on that very narrow range of people. You know, these are all people kind of young to middle age and in their kind of peak physical health and everything. And as we start to look to space tourism as well, we're going to have people with a greater range of medical issues going to space, and then we're going to start kind of seeing the impact that the spaceflight environment can have on those people. But I think the para astronaut call is amazing because it opens up the possibility, and it opens up the kind of realization that space is for everyone. And so what I'd be really interested to see it going forward, to see the kind of the people that come forward for this para astronaut call and how they shape the way that we look at spaceflight and the human body in the future.
Brilliant. Thank you so much for that, Lauren. I think that's going to have to be the end of our Q&A, but Lauren will be joining us on Discord. So if anyone has any further questions, head on over there and Lauren will be happy to answer them.
Yeah.
So next up, we're going to have our kind of closing comments for the conference. We will be back in a couple of minutes to say our farewells.
Hi everyone. We are now going to do the closing for the conference. And it's just been an amazing conference. I just want to firstly say thank you all for coming. I think it's been a fantastic event showcasing such a huge variety of areas of the space sector, discussing topics like really important today, and then looking to the future. I hope a lot of you have been inspired and educated about the opportunities that you can get involved with and hopefully learn something new. Alex, would you agree?
Yeah, so thank you all for coming. We need to just thank our amazing speakers for joining us. We were so lucky to showcase such exceptional people, and there were some fantastic discussions throughout the conference. We also need to say thank you to the sponsors, because without them, it would not be possible to hold these kind of events. Giving the opportunity for you all to network with them is one of the great things about NSSC. And their attendance it kind of shows our support to industry. So just thank you so much for all coming and giving up their time on a weekend. We need to thank the team, because they all did an exceptional job as well. You would be surprised, but a remote conference has more logistics than an in-person conference. So they've all done a fantastic job. A special shout out has to go to Antonio and Aaron for their work on the tech. It's been a stressful couple of days for them, but they've done an incredible job. And it's worth noting that Aaron actually built the conference completely from scratch. Before I hand back to Jacob, there's another person we really do need to thank, and it is Jacob. He's put in a huge amount of work for this conference. He's basically worked full-time on it along with his full-time job. And without his energy, this conference wouldn't have been able to happen. Over to Jacob.
With no energy left now. I would just reiterate, Alex, exactly the same. He's put so much into this. A lot of the new features you see in NSSC this year, Alex's amazing ideas. So huge well done to Alex, and especially Antonio and Aaron for building the Nebula platform. Aaron, that's just so impressive what you've done. And thank you to the whole team for putting on an amazing event. If anyone is interested in working with us in the future, then we're really open to that. If you find out about UK SEDS for the first time, then if you want to speak at an event or work with us in industry with your industry hat on, then please reach out to us. We'd love to hear from you. A feedback form as well has just been sent out to you all. So in your inbox, if you could have a look at that and give us your feedback, we'd really appreciate that, because as Alex has said, this is the first time that we've run an online MSSC. And so we really value that feedback. We are offering a prize, a £50 Amazon voucher to one lucky person who completes that. So hopefully a little incentive for you. That will be in your inbox now.
And so just to my final point would be, obviously remote is not the ideal conference, because we all love the NSSC social and we missed out on that greatly. But some would argue our Sundays might have been slightly more productive than they otherwise would have been. But just a bit of food for thought for you all. We would, without this remote platform, we would have had no chance of pulling in some of the speakers we did. It's worth noting all three of our keynotes were keynoting from other continents. And we, given the climate talk earlier, it wouldn't have been justifiable to fly them all the way out here. So we appreciate it was a hard one with kind of the change in networking, but we hope you enjoyed it. And we were so lucky to get who we did to speak. So I hope you appreciated how lucky we are. This will be my closing moment. So thank you so much to everyone at UK SEDS for my time on exec. I've really enjoyed being part of the team. If anyone kind of wants to get involved, as Jacob said, keep an eye out for our volunteer positions, because there will be some coming out in the next week or two. Thank you to everyone at UK SED, and a special shout out to our trustees who never get a mention, really. They give a lot of advice to us as an organisation and have an awful lot of experience in the space sector. So thank you to them.
Yeah, very good point there, Alex. And I'm sure you're wondering what NSSC is going to look like next year. And we can't tell you that right now. We don't know. We're hoping to learn a lot from this event and potentially see you all in person next year. So your final words from me. I'll echo Alex and just say that this has been the best experience of my life leading UK SEDS this year. And I've really enjoyed the conference, especially, and working with some incredible people. We will now be having our AGM for members, and there we will be electing our new committee. So I'm sure that the new committee is going to bring a lot of more fantastic ideas for UK SEDS to the future, and we look forward to seeing what they do. So I will now close the conference. Thank you all again for attending, and I'll see you next year.
An awkward wave goodbye.
Yeah, bye.